Okay, I think I figured it out. There is apparently a new button I didn't see in the past. So hopefully, just to double check, we are also live on YouTube, and I think we are. Excellent. Right. Let me just close this. And now we can actually formally begin with already a 7-minute delay. So welcome everyone to the 11th Gaia Alerts Workshop, which we now call OPTICON Gaia Science Alerts Workshops. We've been doing these workshops for 11 times already, and it's an honor to host it again. We keep more or less the annual timing here. So I will just show a welcome slide, and we'll cover some very minor technical issues. So this is our poster. This is my welcome slide. And we have more than 100 registrants today at this workshop. This is a very unusual one because we have to do it online, but I hope this has the advantages as well, that we can have people from remote places of the earth joining us here live and talking with us about the exciting stuff we are going to talk about. We will have 60 talks squeezed into those 5 days, more or less 3 hours a day. I hope you will survive. You can always take a break if you have enough, but they all will be recorded. That's why I struggled those 7 minutes to have everything streamed on YouTube, so that everything is available afterwards. So you can come back, and if you miss something, you can always rewind and watch it again. And here is a pie chart showing the participants' countries. You see, we cover almost every country in the world, which is great. And here I, of course, would like to thank OPTICON for the support, ongoing support for these workshops. And we will continue with the support from OPTICON and the new grant as well. I also thank the Polish Space Agency for the patronage, the honorary patronage. But before I let the president of the Polish Space Agency speak, I have to spend 1 more minute about these technical points that I really ask people to keep the time. Most of the talks are 10 minutes, maybe 12 minutes, plus 3 to 5 minutes for the questions. In the Zoom, please try not to interrupt unless there's some urgent technical issue. Keep your microphones muted. Raise your hand if you want to ask a question. You can do it also during the talks, but then turn on your camera and mic on when you want to speak. And there will be the YouTube stream as we are now live. If you don't want this, let me know. We'll try to figure out something. And for the longer discussions, which I really hope there will be, please move to the WonderMe, which is a wonderful tool, which is great for such occasions. And the link, I gave you the link on Slack and in emails. So please join there and have informal discussions, more discussions. There will be some hands-on sessions as well carried on Zoom, on WonderMe, sorry, not here on Zoom. So please see the agenda for details. For the Slack, this is a Slack which is going to be used primarily for Black Hole Tom. You'll find out what it is, but also there is a channel related to this workshop. And the last but not least, there is code of conduct for this workshop. Please read it on workshop pages. If you, by continuing, I assume you accept it, and I will stop here, and I will welcome the president of Polish Space Agency, Mr. Marek Moszyński, which I asked to give few welcoming words. Please.
Thank you, Professor Wyrzykowski. It is my pleasure to welcome you. And there are several reasons why this welcome is particularly important from perspective of Polish Space Agency. First of all, you all know that astronomical research are traditionally driving force behind many space missions, and Poland actually is a moment in which we discuss how many mission and what should be the topic for the first Polish mission are. And that's why we discuss in a frame of our national activity on the selection of such mission. And actually, Professor Wyrzykowski, who you know better than me as an expert in this project, we started to discuss in a frame of a scientific panel of Polish Space Agency how we can proceed having astronomical knowledge and transform this knowledge into the reason why and what should be done in this research area. And particularly, you know that this is the time domain astronomy probably, and you as you deal with this topic, and there are many transients in our life nowadays, especially the form of the conferences were transformed into remote or distance rather conferences. And this welcome is from Gdańsk, where there is a head of Polish Space Agency. Outside is -10 centigrade, and this is not probably uncommon in the universe, but the snow is lying everywhere. Anyhow, I want to wish you a traditionally fruitful discussion, but because of a special topic, I believe that there will be no violent deep sky events through these 5 days, and any disruption events. And I wish you everything which is related with good conferences, obviously without technical problems. So have a good time in this distance conferences. Thank you very much.
Thank you very much. Thank you for kind words, Mr. President. Can I now ask? We'll now move to the scientific core of the meeting, and I will ask now Timo Prusti, the head of science, scientific project manager of Gaia space mission, to tell us about Gaia. Timo, please.
Good afternoon. Do you see the screens at the right order?
No, actually, we see your secondary screen.
Yeah, that's what I was afraid.
Oh. There is a switch button.
Yes.
To the X. Yeah.
Wait a minute.
On the left here, this one. Yeah, we're there.
Yeah, I don't see it on my screen, unfortunately.
Ah, interesting.
Yeah. So I am searching. It's maybe behind. Yes, now I found it. It's behind. Oh, the Zoom wants to put the names on top of the X. There you are.
Yeah, that's great.
Good. Okay. Good afternoon, everyone. So I will give an overview of the Gaia mission and where we are at the moment. And I was sort of assuming that not everyone is totally familiar with the mission and spacecraft, so I get some basic steps done as well. First, to move into the sort of overall mission properties. So Gaia is an ESA-only mission, so basically a European enterprise. We launched 2013, and we had a nominal 5-year mission. And at the moment, we have already completed a 5-year nominal mission, and we are at the 5+ year extension. I come to the dates a little bit later in this presentation. Gaia is located at L2, so far away from Earth, to keep the Earth, the Sun, and the Moon at the same site, so and turn the back to those all. Those are all the harmful things for us. And the main purpose of Gaia mission is astrometry, especially parallaxes and proper motions. But also doing photometry to get the colors, properties of the object. And this is done for more than 1 billion stars. In fact, we are approaching the 2 billion count in the recent data release. In addition, there are radial velocities for more than 100,000 stars, and then many, many other catalogs of spanning from solar system objects to astrophysical properties of stars, etc. The data processing, which is a key element, which also the Science Alerts group is part of, is entrusted to a consortium with some 450 scientists and engineers throughout Europe. And we are in the middle of the mission, as I mentioned, 87 terabytes collected with 166 billion object transits observed so far. And of course, what is here for the community, apart from the science alerts, are the releases. We have done already the first and second one. And last month, we did the so-called early data release 3, where the bulk of it will be released at 22. Just an overview of the payload section of Gaia, which is kind of peculiar, and with two rectangular mirrors looking 106 degrees apart. So this is all determined by the core task of the mission, the astrometric part, and the whole design and the spin motion is determined because of that, and the rest had to adjust to that constraint. It is very peculiar, one focal plane and two telescopes looking totally different parts of the sky. So you can see already that there is some sort of bookkeeping exercise, what needs to be done, that you know where an object was observed. The heart of the Gaia mission is the focal plane with 106 CCDs. And there are a couple of things which are important, something called sky mappers. So Gaia has no pre-knowledge of the sky in advance. It detects point sources, and if there is a point source which is brighter than 20.7, it will be marked as to be observed, and it will be observed in subsequent CCDs. Of course, for the transient object, this means that if your favorite transient object or favorite kind of transient object has been detected when at bright, if it ever gets fainter than about 20th magnitude, Gaia will simply not detect it, not because it wouldn't detect it, but simply because this sky mapper phase of the detection chain considers it to be too faint and does not record any further data of it. The astrometric field is the bulk of it, and it is really white light measurement. And this is, of course, what is really the core of also the photometric alerts, because here you have a very reliable photometry, even with sort of direct calibration, what is used for the science alerts. You have seen also in the alerts the spectrophotometric part, which is done with two dedicated CCDs. And as you mentioned already, that there will be the radial velocity CCDs, which are done to about 16th magnitude, because you need more signal to get reasonable spectra from the transit time. The constraint of Gaia is determined again by astrometry. We need to have an extremely stable satellite. And one of the constraints is that it's kept for always 45 degrees from the sun, so that the thermal impact on Gaia is always the same. Now, how do you then scan the sky with this kind of construction? Gaia is a spinning one, spinning in 6 hours, but the spin axis is precessing, so you get the variation to regular spin by having the spin axis to precess. And of course, Gaia's location at L2 means that we are moving around the sun with a period of 1 year. So this whole thing gives a sky coverage which can be illustrated how the sky is mapped. And the whole way how the sky is mapped is predetermined. So in a way, the science alerts have to live with the fact what it gets from this mapping. And the idea of this mapping is to cover the whole sky as homogeneously as possible, given the pointing constraints to cope with the thermal constraints of the satellite. So as a consequence, the sky is not perfectly homogeneous, but there are certain parts of the sky which will be observed less frequently. And particularly, you see here when the data has been plotted on the screen, that the ecliptic plane is not as well covered as the ecliptic poles. And in addition, at 45-degree ecliptic latitude, you have an area where objects are seen extremely often. Now, where we are at the moment, so operations are nominal. Even during the COVID times, we managed to keep things more or less stable. We had to do tiny little modifications, and after we got used to how to live with the COVID situation, we actually are now perfectly doing operations just as without COVID, no difference at all. We are more than 2,000 days in operation mode. The nominal 5-year mission is completed, and we are now in the mission extension phase. And the latest prediction of how long Gaia will live is we will be running out of the micropropulsion gas somewhere early 2025. And of course, we have to hope that nothing else happens before that. And when the micropropulsion gas is finishing, then we cannot control the spin anymore precisely enough. So it is like a real end to the mission. We cannot do scientifically relevant measurements after that. Where are we at observations? So I was just counting the number of CCD measurements. So we are already at the trillions. And out of those measurements, most are done with this astrometry field, so about 1.6 trillion CCD measurements. And then we have 330 billion spectrophotometric measurements and more than 30 billion spectra. So we don't talk about millions, we are more at the billion domain with the number of observations. Of course, data telemetry down doesn't really help the scientific community. So I mentioned already that there is the Data Processing Consortium, which is pan-European enterprise, 450 people involved, and 6 different data processing centers, which are also outlined in this schematic map. And of course, without this consortium, nothing would be available for the community. The latest one, as I mentioned, the early data release 3 was done in December. And we are talking about 1.8 billion stars with positions and brightness. And about 1.5 billion of those ones have actually also red and blue and integrated photometry and parallaxes and proper motions, which are the objects most used by the community. I will come to the 1.6 million extragalactic sources a little bit later in this presentation. I'm not going to show many slides about the performance. Of course, for the science alerts, you don't need the highest possible quality of photometry because you are looking for big variation. But it is, of course, good to know that eventually, when the data is processed and calibrated in the pipelines, we are talking about extremely high accuracy photometry with well into the millimagnitude domain for very wide dynamic range. Just showing what happened when in 3rd of December, the archive was opened. You can see that within seconds, the number of people accessing, looking for the Gaia data started to approach 300 users with probably ready-made scripts because the number of accesses went into about 10,000. So people were quickly loading data to work on the Gaia photometry and astrometry. We see the same also in the amount of active users. Typically, we have like 5,000 different users per month. So within the first 8 days after the release, it galloped already above 7,500. And of course, people are also downloading data. So we see similar kind of peaks with every release. Lots of people using the data and getting it on board as quickly as possible. I don't go also to the scientific results, but I just show one example of what was done as something called the performance verification paper. So what was detected, it is an impression of the quality of the data that quasars, which of course should have no proper motion detectable with Gaia accuracy, but one could see a pattern of these quasars all having a proper motion towards the galactic center. And of course, they don't have any proper motion, true proper motion to the galactic center. This is all the reflection of the fact that we are around the barycenter and moving around the galactic center. And because we are in an accelerating system, we see this acceleration as proper motions of distant sources. And based on that one, there was the first optical detection of the movement of the solar system around the galactic center. And the proper motion vectors, which I showed at the beginning of this plot, they were, of course, incredibly much bigger than what in reality, because the biggest proper motion was about 5 microarcsecond per year, which is much below the individual uncertainty of these proper motions. So this work was possible only by matching the pattern, what is expected from the fact that we are going around in orbit around the galactic center. So it's a sort of fantastic example of showing the quality of the Gaia data, and also how the data processing systematic effects start to be very well under control. So the data is really getting all the biases also out of it. A little bit of the extension. I mentioned already that we are in the extended phase. So after the nominal phase, how does it work? You don't get automatically extension phase. You have to explain, first of all, that the spacecraft and payload are in technical shape to continue observing. That's the first condition, of course, that you can conduct technically the observations. But the second thing is that what more can you provide on top of the nominal mission? So a rather extended science case was presented for the ESA advisory bodies, and those cases got good marks. And based on that one, this ESA Science Program Committee, where all the member states who decide about the ESA Science Program gave the green light, confirmed the operations to 21-22, and also indicative extension for 23 to 25, which means the end of the mission. So I think we are fine. We can use Gaia till the end and make the maximum use of the capabilities. So just very quickly wrapping it up, I think in conclusion can be said, spacecraft, payload, everything is operating nominally. So we are happy with this one. Of course, the nice thing was happened last Christmas Day. There was a hiccup, and then all the engineers, instead of having a Christmas dinner, they were all at Darmstadt ESOC looking that everything was fine. Actually, it was very quickly fixed, but it's a typical thing. Which day do you want to have a problem in a spacecraft? On Christmas Day, of course. Huge amounts of data continues to be collected, and there is just no end to it for the time being. And the data processing by the consortium is progressing towards the next releases. So we just made a release. The second part is expected first half of 22. And in fact, the processes for the next phase, which will be some years later, have already started. So people are already looking for periods 4 years from now. I showed a couple of plots of the Gaia data in the archives, and you can see that it's really extensively used. It is by far the most used archive in the ESA archive department. And the results are published and presented, and we are typically having, the last years, we have more than 1,000 referate publications using Gaia data per year. So I think we have a rather good evidence that we are doing useful measurements, and the community is happy to use those. And I will stop here.
Excellent. Thank you, Timo. Timo, I'll do the clapping on behalf of everyone, but I'm sure everyone was pleased. So we have time for, well, we have some time. Thank you, Timo, for this. So if there are questions now, please raise your blue hand on Zoom and then ask the question. No questions. I see that you have beautiful logo behind you. That's the new official logo of the Gaia space mission, isn't it?
That's correct.
Excellent. We should all start using it. Good. Excellent. I think we will use this opportunity to move on. So thank you, Timo, for this. And we will now go into more details about the science alerts with Simon Hodgkin from Cambridge presenting the update and status of the alerting system. Simon, are you with us?
Hello, can you hear me?
Yes, we can.
I need to turn on screen sharing.
Please.
Share screen. Okay. And I hope you can see my slides.
Yes, we do.
I hope when I press play, it works. And you
It
don't see
does,
my
yes.
comments. Okay, great. That's good. A good start. So I'm going to give myself a timer, and hopefully I won't run over. And just to thank you very much for the opportunity to give you an update on the status of the alert system that we're running in Cambridge. The names on this slide are the names of the people who either built or operate, and that includes the eyeballing teams, the system. And this nice graphic is going to be included in a forthcoming paper, which you'll hear more about. And it just shows the distribution on the sky of classified transients. So these are the 25% or so of the Gaia alerts that we actually know what they are. And then all the gray dots, we don't know what they are. You see this large concentration in the galactic plane. This is in galactic coordinates. And so I'm going to talk more about that. This system we have relies really on the chain of data flow from spacecraft to ground through the IDT processing. And IDT is essentially turns the data from the spacecraft into positions and fluxes. And it associates these positions with positions on the sky. So from CCD positions, it computes the attitude of the spacecraft. And then it assigns the transits, the positions of measured objects on the sky to sources that were previously seen in Gaia. This is a Gaia-only catalog. And that's the image on the right. It's supposed to give some indication that you can have many transits of a source and they get clustered together and associated with sources. On the left, you see the sky is full of beautiful artifacts associated with bright things. IDT does a fantastic job of masking and flagging many of these, so we're not as prone to problems as we could be. However, some of these get through. And it's the iterative processing that happens for the per cycle releases that essentially does the final job of cleaning these up and really improving astrometry. But the Gaia daily operation and the Gaia Science Alerts operation, which is another daily operation, essentially has to make do with something that is a little bit less than perfect and leads to some false alerts and false alarms. So what we're trying to do is find sources that either are new to Gaia, we've never seen them before, or they're old sources that have changed in brightness. So it's conceptually quite simple. And for all of these, we require them to be at 19th magnitude, G equals 19 or brighter. We also require one other thing, which is to have seen it twice. Gaia needs to have seen it in 2 fields of view. And the kind of events you might imagine these come from supernovae, novae, dwarf novae for the new sources, and then microlensing events, dwarf novae again for old sources. But we're also interested in things that go down as well as up. So it's sensitive to arc or Bohr stars, eclipses, dipping stars, this kind of thing. So we try and be as unbiased as possible and essentially let the detectors tell us if a statistically significant variation happened. But more on that, if I can find the next slide button. Okay, for some reason, it won't let me change slides. What we have is a large number of transits, maybe 10 to the 8 or so, and we need to mitigate these to get rid of the large number of essentially things that we don't believe are variable. And so our first job is detection, to find these classes of sources, and then we try and classify whether these are real or bogus. And so the things that survive our detection per day of order 1,000 things per day or a few thousand things per day. And those go through a fairly aggressive filtering to weed out things that we think are not real events, false positives, if you like, which leads to of order tens of objects that need to be eyeballed. We have a human eyeballing team, wetware at the moment, and that leads to about 12 events that are published per day. And this is just to show the data rates with some scale in it. So the number of transits processed by alert pipe per day is the top gray line. So that's of order 10 to the 8 or more. And then 4 orders of magnitude below that are the number of detections we have, which is in blue. These are the things that alert pipe finds as candidate alerts. The ones that survive filtering are shown in red. And so this is the tens of events per day. And that's what the eyeball is to look at. And then from those, they select of order 10 per day that we publish. And it's currently the rate we publish is about 10 per day. And the filtering took us some time actually to get it right. In the first year of operations, we had to do a lot of testing and validation to get it right. Most false positives are actually environmental in origin. And they arise from, for example, the wings of a bright star, or Gaia's field of view is pointing towards or close to a planet or bright star, a degree away or something like that of a bright star. Or a pernicious sort of cause of flux variation is if a star has a near neighbor. It doesn't even need to be a bright near neighbor. It can actually give us a false signal. We also, at this point, classify things that are known SSOs, solar system objects. Things that have been published by Gaia as known DR2 variable star with some classification. And also to get rid of a lot of false alarms, we reject high amplitude red variable sources that are historically have significant variation. An obvious class of those are the MIRAs. And this is the business about near neighbors. So Gaia has this window on board where it measures flux, which is about an arc second by an arc second. And if you have a source which lines up, and it will do sometimes, a cross scan, and it's just on the edge of the box, then some of the light from that star will creep into the window. So you can get a scan angle dependent variation in flux. And this is this bottom light curve here. Shows a little pop up in brightness when we see a source which is lined up, it has the same along scan coordinate. So all our filters need to get rid of those kind of things. So we publish alerts with a delay, and I'll go to the bottom histogram first. So in the bottom histogram, the median delay is just over 2 days. Our goal was to hit 2 days, but we're a little bit over 2 days, 2.1 days or something is the median delay. And this distribution here, you can see there's this long tail up to 10 days. And that's shown in the top histogram. The top histogram is each dot is one of our alerts, and there's the difference in time between Gaia measuring it and our system publishing it. And that's because we require these two fields of view. So sometimes the Gaia scanning law requires you to wait for the source to become visible again to Gaia, because we didn't get 2 consecutive scans of the source in that particular point of time. We had to wait another 30 or 40 days. And that's why we get this long tail and long publication delay for a small number. But the majority you can see are hovering around 2 days, some are much shorter. In orange, I'm showing the publication, the processing time for us. And the processing time for us, the median is about 4 to 5 hours for our operation in Cambridge. And so this is the rate versus time. We're currently nearly 15,000 alerts since November 2014. And we have these different phases where we got better. So initially we were publishing at 1 a day, where we were learning how the spacecraft worked, what the data looked like. And after that, we improved our software and turned it back on again. We initially were masking out areas of the sky, the galactic plane, basically, with a density map to say the alert rate's too high here. We don't understand how to filter it. But we improved our environment filters and could switch that off. So now we don't mask out any of the sky. And so by the middle of 2016, we were operating a smooth system, which has been fairly stable, entirely stable, actually, since beginning, middle of June 2016, with a rate of 6 per day. And then we just added improvements. So we did better at filtering out some of the high amplitude variables, and that allowed us to push a little bit into the noise. And then Then we added in a new detector, which is sensitive to slowly varying objects, which we call the skew von Neumann detector. So the photometry is very precise. At 15th magnitude, our photometric precision is about 1%, and at the detection limit, it's 3%. And this comes from DPCI, the IOA CU5 processing team built a photometric one-day calibration. So it has a cadence of 1 day, and we update our calibration on a roughly monthly timescale. So it means at the point of publication of an alert, the photometric calibration for today's data is actually slightly out of date, but Gaia is so wonderfully stable that the change in that is not significant, not dramatic. And then as the calibration is updated, then we update all the data we publish. So the data we publish two versions, one which is static and stable, another one which is dynamic, which is the one you see on the web page. The astrometry is accurate to of order 50 milliarc seconds, so that now Gaia is the, if you like, the ground truth for all the transient surveys. And so if we've seen an event, then the astrometry that's publicly available is updated to the Gaia measurement for that source. And that's after extensive testing by the transient name server of all the different surveys. And they concluded they should use the Gaia astrometry, which they do now. Gaia is an all-sky transient survey, one of the few. Most have holes in the galactic plane where they avoid regions of high density, or they're stuck with being in one observing site, one latitude. And so they miss either the southern or the northern hemisphere, depending where they are. Assassin has a multiple site observatory, and so they're able also to go whole sky, and those two are quite comparable in that sense. So of what we publish, and given that 25% of them roughly are classified, then what can we say? And the classifications are published. We have to scrape a lot of different sources to get hold of these classifications, and for the those published with classification supernovae dominant. And this is because there are dedicated supernova spectroscopic follow-up programs. And so these surveys mean that we see almost 60% of the classified alerts are supernovae, followed by AGN, CVs, young stellar objects, and then a rough collection of other things, which microlensing events are in that bucket. But because the nature of the follow-up programs and the scarcity of resources, we shouldn't necessarily extrapolate these to the 75% of unpublished alerts. And so to demonstrate this further, these are on the left-hand side, everything with their classification plotted in galactic latitudes, contrasted on the right-hand side with everything without a classification. And you can see they're anti-correlated. So the majority of unclassified alerts are galactic in origin because they sit close to or in the galactic plane. And so the statistics in that previous slide can't be extrapolated to they're not reflective of the true breakdown of the transient classes in the Gaia Science Alert. So most of them are galactic in origin. And we did a bit more digging on this. So on the left-hand side, we made a color magnitude diagram of every alert that was published that had a counterpart in data release 2, and therefore with a parallax. And so all the things classified as CVs are shown in blue, and all the things classified as young stellar objects are painted in red. And so the idea here is, could we build a simple binary classifier between these two different classes of objects? And we could, and the right-hand side of the figure shows essentially this the results of probability density map of the classifier applied to 815 unknown alerts which have parallaxes. And so as a result, we end up with essentially, depending on where you set your probability threshold, of order 800 new candidate CVs and of order 400 new young stellar objects, which will all be published quite soon. We've also tried to measure purity of the survey. We've argued that we're quite good at throwing away garbage, so we tried to test this. And in this plot, we plotted minimum purity as a function of galactic latitude. And to measure this, we decided an alert was real if there was some external information which supported it. So somebody else classified it, or somebody else published another transient at the same place on the sky, either before or after we published it. And so if so, then we said, well, this is a real astrophysical event. It's nothing to do with artifacts in Gaia. And so this minimum purity, we then investigated regions of high galactic latitude, which is shaded on the right, and low galactic latitude in the middle. And you can see the purity, minimum purity, drops to 10% there, because there are very few classifications or external surveys happening at low latitudes, whereas at high latitudes, plenty of other people are looking close in time and classifying things. If we restrict this to, instead of G19, which the plot is for G17, then this minimum purity increases to 0.93. And so we did a lot of extensive investigation, and this is all going to be published very soon. But this is just an example of the kind of investigation we're doing. The left-hand plot shows essentially all neighboring sources for published alerts outside of 0.2 arc seconds, but within 2 arc minutes. And essentially all you see are there are no artifacts AL and AC, so a long scan and a cross scan, but you do see a cluster of sources which are not the alerting source close on the position of the source. And so these are the detections of the galaxies, which we quite often see in Gaia underneath or close to the alert, the supernova event in the high latitude sample. On the right-hand side, we did the same exercise, and here there's no near neighbor sources, and there are no artifacts AL and AC at low galactic latitudes, so mod B less than 8. So we find no evidence that alerts in the galactic plane suffer more from artifacts than those at high latitude. And we find that the fainter alerts are just as reliable. So we did this, sliced it up by magnitude as well. And we find no difference as a function of magnitude. And so we propose that the purity of the alerts we publish is no worse than that of the high latitude subset and the GMAG less than 17 subset. So we think our purity is close to 93% or higher. That's the minimum purity. We've also measured completeness for supernovae. Now, it's hard to discuss completeness of a survey because different classes of events look very different, but supernovae we took as a sample that we could test. And so these slides show a little bit of investigation of completeness of a supernovae. So the first thing we did is the graph on the bottom shows the histogram of the number of TNS supernovae that we didn't detect is shown in red as a function of the number of times Gaia looked at that point in the sky within 40 days of the event being published by TNS. And then in blue is the ones we did see, are the ones we did see. So you can see there's a strong dependence in whether Gaia published it, detected it and published it on the number of times Gaia observed it. And the completeness curve, which is on top in black, suggests that below having fewer than 2 scans means that we have a poor completeness, whereas above 2 scans, our completeness is 0.4 and rising to 0.8, depending on the number of times we see it. This is not surprising. This is what we expected before the mission. But it does show that the scanning law and our 2 field of view requirement dominates the completeness of Gaia. So our external completeness on average is about 0.46, so a little under 50%. We investigated a little bit further. So as a function of magnitude, we asked, does it fall off to faint magnitudes? And so the same exercise, but now for those that have at least 2 detections in Gaia. So we have a smaller sample now of supernovae, a little over 1,500, with more than 2 scans or 2 or more scans. And our internal completeness for that sample, we call it internal completeness, is nearly 70%. So if we have 2 or more scans. And there's no strong trend with magnitude. There may be a slight roll-off. It's hard to tell if this is arising because different surveys use different filters, but also that sometimes the supernovae discovered are actually fading at the point of publication. And so that may also be playing a role here. The other thing we considered is the proximity to the galaxies. So we use the 2-mass extended source catalog as a sample of galaxies, and we cross-match the Gaia alerts against those. And again, the same, the TNS supernovae against those. And the same exercise, did we or didn't we see it? So blue, we did see it, red, we didn't see it. And here we see a drop-off within 3 arc seconds of the galaxy position. So beyond that, the completeness is very good, but it's clear that within about 3 arc seconds, then we're starting to get confusion, and the Gaia alert sensitivity is not performing well in these more crowded and complex regions of galaxy nuclei. So I'm going to wrap up with 2 more slides now. The things that are on the kind of horizon, we're investigating, can we publish alerts that are discovered solely in a single field of view and improve our completeness to transient events. And the motivator for that was gravitational wave sources. So Susanna will talk about this on Tuesday, and it's published in the paper last year. The other thing we're trying to do is take out the human component, make the system fully automated. And Gabor Martin will talk about that on Wednesday. The paper is almost finished, and it's been shown to the DPAC executive. We have some comments, some very constructive, helpful comments, and they're all nearly sorted now. And then we're going to circulate it to all the authors to secure their consent. The author list includes many of you here who've helped us on the way to build this, and so we're trying to be as extensive and inclusive as possible. So you should expect to hear from us with a draft of the paper quite soon. And DR3, which is coming in a year and a bit's time, will include, so all the data releases from Gaia will include the alerts in the appropriate cycle from the next data release onwards. And so my summary, we handle 60 million measurements per day. Have I got time to say this, Łukasz, or should I just leave it up?
Yes, you still have time. Please.
So from 60 million measurements per day, we look for new sources and sources which change significantly in brightness. The detectors work with the light curves rather than doing just differences between first and now. And so it's sensitive to things that change gradually. We run a series of mostly environmental filters to reduce the detection rate from a few thousand potential candidates to a short list of tens per day, and they're eyeballed. Our accuracy is astrometric is good to 55 milliarc seconds, and photometry is good to better than 3%. We publish 12 events per day, and 25% of them will receive classifications. So we need to do work on understanding what most of them are and find the really, really rare, really interesting things. Even though the published classifications are dominated by supernovae, this is biased by the nature of follow-up for scientific reasons and for good reasons. But the bulk of our unclassified alerts reside in the galactic plane. Our contamination rates are low. We argue that the minimum purity for our survey is 93%. The completeness to supernovae is 46% across the whole sky from our experiment. That doesn't mean we can extrapolate it to shorter duration events. And so that would need to be worked out separately and be quite a significant undertaking. But we're dominated by the scanning law and our requirement for 2 field of view detections. The completeness beyond, once we've had 2 scans, is 80% nearly, unless we're right in the centers of the nucleus of a galaxy. I haven't said much about the reasons why it breaks down there, but it's to do with having multiple source IDs within the same area and confusion with detection of the galaxy itself, which has made our job rather harder. And then for the alerting sources included in Gaia Data Release 2, we've run a simple classifier, which has led to a production of a new catalog of something like 800 new candidate CVs and 400 new candidate ISOs. I'll stop there. And thank you very much for your attention. And thank everybody on this list for all their help over the years.
Okay, thank you, Timo. I see Sri wants to ask a question. Sri.
Yeah, hi, Simon.
Hi.
It'll be really useful if the alerts can make classification between transients and non-transients better. I don't mean parochial. It's just if it's transient, you want to get around to it or not. If it is a variable, okay, you got time. So why don't you take your alerts, and now that the force photometry service is available both from Atlas and ZTF, and just check if it is a known. It's a known meaning it's a variable, maybe unknown as in not in SIMBAD, but known as in the sky. Then if it's got past behavior, okay, it's another star that's just burbling along, and then we are done.
I agree, and you made this point in a paper, and I think I don't know if there is a TNS representative here. I don't think there's a flag which would allow us to tag it as such in TNS. At the moment, we submit everything to TNS, so it'd be nice if we could label them exactly the way you suggest. I agree.
Yeah, maybe we could use this meeting as an excuse to get some letter to TNS, because this is causing a lot of confusion and heightened expectations that I hope the Gaia team has the ability to fill, but the TNS doesn't seem to have the ability to accept. And
yeah, we do.
Hopefully some yeah, go ahead.
We publish a light curve on our website for everything, and it's machine readable. It's absolutely scrapable. So you can see straight away if it has a history or doesn't have a history. And we tag them as a new source or an old source. I do agree, though, having the force photometry tied in would be very useful for the hemispheres that's available. And that's something we could add in. Development costs aside.
Thank you.
Yair.
Yes, hello. Thank you, Simon, for the presentation and in general for all your work on the Gaia alerts. Actually, now I also wanted to ask Sri, he mentioned the ZTF force photometry. So this is my first question, is this indeed already available?
Yep.
Great.
That's really cool.
Yeah, I believe it was announced at the AAS. I've not been keeping track of it, but if you send anyway, it's available.
Excellent, that's great, thank you. But Simon, I wanted to ask you about this completeness in galaxy nuclei, which I find very concerning. Is this with these? I remember your group, I think it was Susanna, had this more sophisticated algorithm for things in galaxy nuclei to avoid all of these confusions and some of the splitting of IDs. Is this with that algorithm implemented, the completeness, or is this before that?
It's independent of the algorithm, and we haven't applied Susanna's approach. And Susanna's approach was to cluster all the detections within a radius of the center of a galaxy, a known galaxy, and treat them as the sum total flux in the center of that galaxy. And that would get around this problem, because the problem we have at the moment is the trouble is the design of our software is led by source identification. And so we'd have to redesign the whole system to do this clustering analysis and integrate the fluxes across the many component sources that the initial data treatment quite recently are arguing are separate, because most of the time they would be. So it's something we'd really, really like to implement. I'd love to do that, but it does require significant extra effort and redesign of some of our systems. So, yeah. Okay. So the number we found, the missing fraction right in the central arc second or two, is very close to what Susanna did when she was looking for tidal disruption events and finding the same problem, which is in the centers of galaxies, the alert system is missing things.
Okay, thanks.
Okay, Gabor?
Hi, everyone. I don't have any question, just a comment, because I believe that according to the last version of the agenda, I will talk tomorrow morning, not on Wednesday, as you...
Apologies. I didn't read the latest version. Sorry.
Yeah, that's all I just wanted to say. Thanks.
Okay, thank you. Thank you, Simon, and thank you for all the questions. Actually, I might have one comment to this. Is that even though Gaia completeness seems kind of low, we miss those supernovae, and many people working on supernovae, they say, well, we have all those supernovae from other surveys. We have them we found within first hour, while Gaia gives them after 2 days. But I would like to remind you that Gaia gives, apart from the detection and measurements of brightness, it also will eventually give you the superb astrometry of the alert. This is very unique, and this is good to keep in mind that the astrometry of the alerts is also coming in the final data release. Is that right, Simon?
Yes. I mean, I'd say yes. So I hope that every transit in the sky will be astrometrically calibrated onto the same system and will then be published. And we'll also have the spectra. And this was a question that was asked recently by the Bright Transient Survey Group, which is, will all the Gaia spectra be published at the end of mission? And my understanding is every single transit will be published at the end of mission. So all those spectra will be publicly available too at the final data release.
Exactly. Shri, you have a comment?
Yeah, so as you know, the SCDM, which does about half the classifications of the supernovae in the world right now, is an R of 100 spectrometer. So if you combine your BP and RP, I think I'm not sure I understand. Anyway, both are prism spectrometers, okay? That sort of in the end, it'll have the same spectral resolution. So the part that I must say I myself have been surprised is that even with a lambda of delta or lambda of 100, we are now able to do very clearly, of course, 1A versus not 1A, but including subtypes. So I hope your team will dive into it once you calibrate your BP, RP, whatever. Once you get over that hurdle, there may be surprisingly rich information, even though the resolution is poor, based on SCDM, which is hardly a comparison in stability to what Gaia is.
Yes, absolutely.
Okay, great. Thank you for this talk, Simon. And I hope we will continue the discussions on WonderMe. I do encourage people to, well, not now, but after all the talks and tomorrow morning and tomorrow, throughout the whole week, to move the discussions in more detail to the WonderMe tool. It's like Zoom, kind of, but you can talk to selected people, not to everyone. Right. So let's now move to different kind of talks with Jerry Gilmore first presenting what OPTICON used to be and now what's the future of OPTICON. Jerry.
Good afternoon or morning or wherever you are, everybody. Let me try and get this to share. I am screening, okay, and do a Control L. Can you see what my screen?
We do, yeah, now it's in full screen.
Okay, good.
Yeah.
Right, so I'm going to give you an overview of what OPTICON is and what the future holds for the strategic and funding and so on context of what's going on here. So first I'll give you a brief overview of OPTICON, which has existed for the last 20 years, but is soon to end. And it's merging into a new future called the OPTICON RadioNet pilot that starts in the beginning of March. So, and what is the connection of this to Gaia Alerts? Well, Gaia Alerts follow-up science has been part supported and developed by OPTICON since the launch of Gaia. Now, this is the follow-up science part of it, that sort of stuff Simon was talking about. All of the huge Gaia data processing pipeline activities and so on, which is an enormous opportunity and challenge, hundreds of people, that's funded by the various national agencies. So Gaia is just doing the non-agency bit to turn it into something that's useful for the community. And we did this partly because of an ambition across Europe to develop time domain astronomy starting some years ago, partly for strategic reasons, because it was realized this was a good way to bring Europe together, and partly because it was an obvious developing branch of scientific research. So the bit that OPTICON sponsored was the data processing, the calibration server, the spectrographs with their rather stupid names, the networking, and the alerts pipeline stuff and so on. And in addition, there's a substantial amount of telescope time funded competitively through a time allocation system, which will be talked about in the next talk by John Davies. So OPTICON started in the year 2000, same year that Gaia was approved as a mission. It was very widely supported across Europe, particularly in the early days, because it's funny to think of it now, but 20 years ago, European astronomy was very much less integrated than it is now. And so this was part of a strategic move by a lot of agencies, particularly the EC, to try and get people talking to each other and collaborating and becoming good citizens. And so you can see there the list of always a large number of partners. The partners were national funding agencies, hardware development groups, observatories, and industrial partners. And the goal was to provide partly observing access, so that's competitive telescope time by buying the time from the telescope owners. A lot of early readiness level technology research and development for future instrumentation and telescopes, and also a lot of networking and community development. And I'll give you a couple of examples of that. But first, where we are right now, this is our current, the project that's currently running that will end in June. And you can see the top half of this slide is technology development programs. The middle bit through the middle here is community development. And the science bit is the bottom two corners. So this is the transnational access, buying telescope time for the next talk. And off down the bottom left here is Vukash as we empire. And so this networking bit you can see in a little bit more detail here. We've always supported the adaptive optics community development. It's been clear for decades that adaptive optics is a necessary future for high precision and large telescopes. Number two, we've always supported high frequency interferometry, optical infrared interferometry, which is mostly focused on the ESO VLTI, but far from totally. And we've also always invested in training schools, number three here. So this is for the young people. And then time domain astronomy. So you can see time domain astronomy has been picked out as of comparable importance to the technologies which underpin the whole of the future large telescope structure. So it's got a very high profile in OPTICON and has done for some time. So now briefly going back to what we've done over the years, OPTICON was originally, as I say, set up to try and strengthen European astronomical community. It's worth remembering that quite a lot of the large countries were not members of ESO at this stage. So European astronomy was just coming together. And the EC was, the European Commission was only just starting to fund scientific research and technology development. They hadn't done it before that. And so this was early days for that combination of things. And so the sorts of projects we had initially, I shan't read all the words, was a mixture of strategic development for the future and implementing technology skills into what turned into the big database systems that we have just been talking about. There's a lot of the early work for that was done through OPTICON. And then building large-scale community bottom-up projects, which was the ELT. And the ELT is probably worth mentioning because I think it's our biggest success story. Because it started at our first board meeting. We resolved that all the partners said, okay, we should develop a case for the ELT. And so OPTICON, under my leadership, then negotiated agreement between all the various projects that were going across Europe at the time, brought them all together into a single project, set up a design study, which I chaired for the next 5 years, set up a team across Europe, but also including ESO, and Catherine was the ESO Director General at the time. And then this led to a project which I presented to the Combined European Strategy Forum for what became the ELT. So if you look up the European Strategy Forum, you'll find that I am the lead on the ELT, which is ridiculous because it's ESO really. But anyway, so that was a nice example of a bottom-up community program that was very, very successful. And then there was all this other technology stuff that we did as well, and strategy stuff. The adaptive optics technology, I've got the next slide, I'll show you what that one. OCAM is a kilohertz zero noise fast camera, which is the heart of the wavefront sensing for the ELT and the TMT actually, and also led to a quite successful spin-out company selling fast cameras. And then all these various other things that we've done as well, including briefly providing a home for the solar astronomy community before they got critical mass and went off on their own. And so bottom line is that we've always tried to be good Europeans in spite of what our governments are doing. Here's one example. This is an instrument, a very successful science instrument on the VLT, ESO VLT, called SPHERE, high resolution imager. And the key to SPHERE is this stuff up in the top right, these very high order adaptive optics system, which allows precision imaging of exoplanets and things like that. You can see some images down there. But over the years, OPTICON provided about 1/3 of this technology, which is a lot of effort and a lot of money, and allowed it to be done at a European level rather than simply 1 or 2 groups, which is a huge advantage of this structure and style of operating, is that we can get people to collaborate as well as to compete. There are a few other things that we've developed. This is some interferometry techniques, which is going to be a big part of the future, as people have learned from the intermediate stage of ALMA that basically the techniques that VLBI radio have now mastered can be applied at high frequencies and can indeed be applied at very high frequencies. And so there's a lot of future there that we'll be seeing over the next few years. And this is some of the technology, this development. I mentioned OCAM, you can buy these things now, as well as them being in the ELT. And there is this large experimental lab, which is literally the size of an ELT. It's got the William Herschel telescope at its core, but it's got the ESO guide star lasers parked around the outside as well. And so you can use this to test out the various types of adaptive optics systems and develop algorithms. And there's also been a lot of work done on photonics, and that again has led to little spin-out companies very successfully. However, it's a feature of success that politicians decide they want to change it and do it differently. And so the EU has now decided to change its model of funding communities like astronomy. And so they've set up this new project, a pilot, for us to work out for ourselves, basically, how we're going to be able to do this in future, but with a big focus on virtual and transnational access provision. So provision to telescopes, time to research and data. Don't worry about all this jargon here. This is just EC stuff. It means we'll carry on roughly as we were before. But also they want us to look at ways of becoming viable without their continued funding. An early guess is that that's not possible because you can't do stuff without resources, but we'll see. So one of the tasks we've been given. And so this is the we're a big thing again, 37 partners across the whole of Europe. It's coordinated this time by Jean-Gabriel Cuby from Marseille on behalf of CNRS. Budget's okay. That starts on the 1st of March. And it is a merger of OPTICON and the radio astronomy equivalent in Europe, which is called RadioNet. And so basically they've just merged all of us together and taken out most of the technology development, the hardware technology development. But there are still development activities in there. The first one is the strategic plan for the future relationship between the European Commission community and astronomy. And that's important for everybody for decades to come. So we have a lot of work to get that right. This is the one that's most important for you in the audience. The goal here of this JA2 is to allow a system which provides an astronomer or a consortium of astronomers with a single proposal, single point submission system where you can ask for as many different facilities across as many different wavelengths and across as much time as you want. So instead of having multiple hurdles, multiple tacks and all this sort of stuff, you put in a single proposal and say, I want 600 nights on 47 facilities over the next 3 years. And it'll be paid for if it's a good enough proposal. And then there's also a lot of effort to develop the gravity instrument on the ESO VLTI, which is spectacularly, has spectacular potential, very, very high resolution imaging system with fantastic astrometric capabilities. And it turns out it's possible to extend its guide star limit by about 5 magnitudes. So that's being done over the next 2 or 3 years, and then will be made publicly available. And then there's 2 big work packages. One is the one you'll hear about in the next talk. That's 3 million euros for just classical CTAC time. And then there's this one with the long, ridiculous name, which I think means something when translated from Polish, but I'm not quite sure. So this is just a list so that you can see all the telescopes, basically. This is the stuff I've just told you about. Then there's all the radio telescopes all the way down there. And then there's the interferometry. And then there's normal optical telescope time. There's technology test beds, and there's the time domain. So I'll just talk about 2 of these because the rest of it's not relevant to the present community, but you can ask, and we'll have a web page up and running and all these things fairly soon, so it won't be too long. But the key of this, which is a big activity, nearly €1 million going into providing this software system. And the ambition is to deliver this new single sign-on. So single sign-on, single access for multi-facility, multi-wavelength science proposals. And this, of course, is everybody's goal. I mean, a lot of people, it's to turn all, not all, but a very large number of the available big facilities into a single point capacity for doing scientific research. And it is the perfect complement to what I'm going to talk about next, which is Vukash's project. So this is a new software control system, an organizational system and data handling systems and so on, which will link into all of the existing big expensive facilities. So this isn't what you'll hear about in a minute. This is the existing facilities that people compete for through telescope assignment committees. The idea is to put them all together, and so there'll be basically a single big spider at the center of the web, and you'll be able to get at the entire web from that. And this is led by Rob Beswick at Jodrell Bank. And there are 16, it's a big activity, there's 16 partners, there's 16 organizations, not people involved in developing this. It's very ambitious, but we anticipate having it running at least in beta release form by the end of our contract. Then there's the complement to that. So instead of big expensive facilities, you have little cheap facilities. And you have very large numbers of them, and you have them everywhere. And then you can just fill in phase space in time. And this is what's led by Vukash. You can see we've given him a okay budget. And this is led from Warsaw, but with a lot of activity both in Cambridge and in Concolly, particularly with Gabor, who's going to talk tomorrow in Concolly. And this is the bit that includes the Gaia Alerts follow-up. Oops, didn't mean Gaia Alerts, I mean Gaia Alerts follow-up. The Gaia Alerts is owned by Gaia, by ESA. It's the follow-up that we do. And so the idea here, and I've emphasized the keywords in the middle, this is virtual access to a suite, a very large number of distributed telescopes all over the place, some of which are robot controlled, some of which you just get access on the time to, some of which you get access to the data from. But the key idea is to build on the successes of the present system. And one of the main successes of the present system is the Cambridge calibration server. And so the idea is to manage all this stuff by, first of all, I suppose someone's going to talk about this, but first of all, to prioritize and select the transients which are appropriate for a particular facility, particular telescope to go and look at. This is the TOM system. Then to provide some continuity, so there's long-term multi-wavelength monitoring, so people don't get bored with an object after a week and go on to the next one. But also, most importantly, is to take these data sets as fast as they can be made available, preferably directly from the telescope, process them, calibrate them, and release them open archive science ready, with the goal of doing that in the same night that you're taking the data. And so this stuff is then an open archive. You don't have to write proposals to access this stuff. We pay it and operate it, pay for it and operate it, and provide the data to the whole community for free. And then the extra part of this is, well, you can never have too many telescopes. And so you want more and more of them to fill in the gaps in the network around the globe, north and south and wherever. But best of all, you want ones that don't require someone sitting out in the cold and having to answer a telephone, because it's quicker and easier to do it with a robot. And so this is the TDA CCS program. So in summary of all that lot, for the last 20 years, European astronomy has benefited from a great deal of European Union money, not just in optical and infrared astronomy for OPTICON, and not just in radio astronomy for RadioNet. There are smaller but still substantial programs in high energy astrophysics and planetary astrophysics and various other things. I think there's one in cosmic rays. And so all of these things, our requirement is to come up with a plan for all of these different things to be able to talk to the EC through a single interface. And so it's a sort of an ESO type in terms of range of activities, but much, much smaller. It doesn't have its own staff, things like that. And so what we've managed to do so far is community building. So we've been able to develop things like the Sphere facility, did much of the background to turning the Strasbourg CDS into the national facility status that it's got now, rather than just local. We're a key factor in getting the ELT approved. Also in developing the plan that led many of the medium-sized telescopes to be moved into survey science for Gaia follow-up and for time domain follow-up. So that I think probably most of it would have happened anyway, but it was coordinated through a plan that was developed through OPTICON in the early days to make sure it all fitted together. So that was this thing here. And then although we, like the Gaia pipeline, don't do the science ourselves, it allows an opportunity to support and motivate and allow other people to work on particularly a European-wide and a global scale. And I think this is probably our greatest advantage. Remembering it's easy to look back on what Europe was like when the Berlin Wall came down and look at what we're like now, and we grumble, but nonetheless, we've come a long way, and it's been a very, very positive step in every possible way. And so there's a good future to continue doing that even better. So I'll stop there. Thank you.
Excellent. Thank you, Jerry. Are there questions to Jerry about OPTICON? Yair, please.
Yeah, I don't know, maybe it's a question for you, Łukasz, about this working group 18, this work package 18 central coordination thing. Are we going to hear about it more, or can you say a bit more about it?
Well, there will be many talks related to this. I will do the introduction today after the break, and there will be more details, more technical details about this stuff. Yes, this is the place. This is the workshop to talk about.
Okay, thanks.
Paweł.
Yes, hello. Thank you, Jerry, for your presentation. My question is very short. Could you tell us when the new pilot project will start?
Yes, well, I found that out myself only about an hour ago. So here's some news for you. Yes, it'll be the 1st of March.
Okay, thank you.
Excellent. Yeah, Paweł has been part of OPTICON, and now is going to continue with the ORP as well. That's why he's so keen to find out.
Recognize Paweł's name as well as his nice smile.
I hope to work within this project. Yeah.
Right.
Yeah, sorry about the delay and not being able to tell people that, but we're negotiating on a daily basis with the Commission to get the contract in place. And so we learned that just today.
Is it the 1st of March or sometime within the March?
No, 1st of March.
1st of March. Okay, good. Okay, any more questions to Jerry or to me? No more questions? Good, let's move on. We are good in time. Thank you, Jerry. Now we move to John Davies, who's going to tell us more about OPTICON and especially about the transnational access and time domain aspects of this. John, are you there?
Yeah, I hope so.
Yeah, we do see you.
Yeah, hello, my name is John Davies. I'm a staff astronomer at the UK Astronomy Technology Centre at the Royal Observatory, Edinburgh. This is the second of these talks I've been unable to come to. The first one was aborted in December of 2019 when my central heating system broke down the day before I was supposed to leave. And now we have a global health disaster. So never mind, I'll get to another one of these meetings one day. So I'm just going to briefly talk about the transnational access element of the overall OPTICON RadioNet pilot. If any of you were at the EWAS virtual meeting, I'm going to say more or less the same stuff that I said then. So I'd go and get a coffee now if I were you. I'll see if I can share my screen. I've only got about 9 slides, so this shouldn't take too long. Share screen, where's that gone there? I want to share this one. I want to go to slideshow. There we go. Okay, so you should see me in a plane and my title slide. Make this go away so I can see what I'm doing. Okay, so this is optical transnational access in the OPTICON RadioNet pilot. I'm going to say almost nothing about the radio astronomy bit. In the first year or so of this new activity, we're going to carry on more or less as we have done under the existing OPTICON contract. So for the next 2 calls at least, things will be more or less the same, and only once the work of that joint activity which Jerry talked about has made some progress towards making a more wider coordinated network, we will transition into some new arrangement. So these are the suite of telescopes which are in the OPTICON RadioNet contract. It's very similar to the one we had before. The 2 main changes are that the Isaac Newton group has dropped out because they are busy commissioning WEAVE and doing other things on the Isaac Newton telescope. And we add the South African Large Telescope, the sort of 11-meter segmented telescope in South Africa. So all of these telescopes are available to you through this program. And this is the way we do it at the moment. So at some point this will change once we get the merger with RadioNet more underway. What we do at the moment is we have a single common time allocation committee, which we call the CTAC. It has 7 people on it. There are 7 scientists from 7 different countries, and they allocate time, excuse me, across the whole network. We use a single proposal system, which is called Northstar, and ironically, it was originally developed under an earlier RadioNet contract, and it was then adapted for OPTICON use. It's starting to show its age. It will be replaced at some point during the ORP, but for the moment, that's what we're using. I want to stress that the OPTICON RadioNet Transnational Access Program is open to everyone. There are no longer any restrictions on the nationality of the PI, so it is genuinely open to everyone. The only minor consideration is that only 20% of the time can go to non-EU projects. So if you're coming out into us from outside the EU, you have to be of particularly high scientific merit. So we solicit proposals, we get them all in, we have them refereed, and then we rank the programs. The TAC, I sit on it, but I don't vote. The TAC organizes all of these proposals in scientific merit order. And then I work my way down this list of ranked proposals until I run out of resources. Now, those resources might be the number of nights which a particular telescope has offered me. If, for sake of argument, Canada, France, Hawaii telescope offers 4 nights, and the top 2 ranked proposals happen to both be for CFHT, then we run out of CFHT nights very early on. Or it might be the amount of money we have, because each of these telescopes receives a financial contribution for the nights they give to our program, and that financial contribution is constrained. So I work my way down this list until I run out of resources, either nights at a particular telescope, or more realistically, the amount of money that's available for me to pay for these nights. So the telescopes receive these user fees based on the demand from the community and the scientific quality of that demand. There are no predefined quotas. There is no guarantee to any telescope that they will get a particular number of nights. So in theory, at least, the user fees follow the best science. If you look at the statistics over the last 10 years, I haven't updated this in the last year, but I doubt it will have changed very much. In this first period up to the end of 2019, we had just over 1,000 proposals to our time allocation committee. 800 and something of them came from countries which were in ESO. 113 came from countries outside ESO, and then the other 36 came from other places. And these are statistics of the success rates. If you are living and working in a country which is currently a member of ESO, you get about a 1 in 3 success rate. Outside of the ESO, it falls to about 1 in 6. And for non-European countries, it's somewhere in between. So the success rate does seem to be somewhat dependent on the experience of your community. However, this is a histogram which I made. The top half shows the nationality of proposers, of the PIs of all the proposals, and the bottom graph is the nationality of the PIs who receive the most time. And you'll see that there's a pretty rough one-to-one correlation. So the countries which make the most applications, it's actually the UK, tends to get the most time. But you also see the Germans make quite a lot of proposals. They also get a lot of time. So if I wanted to say this scientifically, I would say that the success rate is roughly correlated to the number of applications you make. If you want me to put it in street talk, if you don't ask, you don't get. So the reason that some countries get relatively small amounts of time is they make relatively few applications. I'm satisfied in my own mind that this is not a nationality bias issue. We've looked at this very hard, and it doesn't seem to be the case. We have, our TAC is drawn from all different countries, and I've been in all of these meetings, and I know that people have worked really hard to try and make sure there aren't any unintentional biases. The way it works is we have a call which goes out. The next one will go live in about 2 weeks. So the next call opens on the 1st of February, thereabouts, and will close on the 1st of March. It looks something like this. It gives a list of telescopes, tells you the number of nights, or in some cases hours, which are available on those telescopes. The observing semester for those telescopes, they're not the same for every telescope. We don't yet have Europe sufficiently well organized that all semesters are the same. So, but please look at the semester list before you write an application. And then there'll be some notes which tell you that illuminizing is going to take place, or that such and such an instrument won't be available. And these, for the moment at least, will continue to be on the OPTICON website, astroopticon.org. It will move to the ORP once the ORP is up and running. Now, your old time, this is a time domain astronomy meeting. So these are some examples of the time domain projects which have been approved via my Common Time Allocation Committee over the last couple of years. They include all of these things you see here: supernova follow-up on a bunch of different telescopes. The ePesto PI has had time virtually every proposal round for about the last 2.5 years. There's quite a lot of Gaia transients, fast radio bursts and stuff like this. And a lot of these are done in triggered I mean, the robotic, some of the telescopes are robotic, so they can be scheduled in a queue anyway. But quite a lot of them, like the supernova transients, are triggered where we allocate somebody 5 one-hour slots, and they have to contact the telescope to trigger them specifically. So we have both robotic reactions, we have phone the telescope type overrides, and we have regular monthly monitoring kinds of things. So we can do all of those sorts of services within the OPTICON time domain system, within the OPTICON TNA system. It depends how the telescopes individually operate. And here's the future of what we hope to do over the next couple of years. We will continue to hopefully offer access to this network of telescopes, including the new telescope Assault 10 meter. This is quite well suited to transients, by the way, because it's all service observing, it's all queue scheduled. We will, as Jerry has said, once the NA2 gets its single submission system working, we will start to offer joint projects with radio telescopes via some sort of multi-messenger single submission system. We're also looking in, as Jerry has said, about new ways of doing this, using small telescopes, robotic telescopes, telescopes at university communities. You're welcome to contribute ideas to this. My TAC changes a couple of people every 6 months, so we're going to need some new people after 2021B. I expect at least one more person to retire at the end of 21B. So if you're interested in that, let me know. And the next call opens in about 2 weeks. So it's time to get your thinking hats on if you want to propose to that call. And that's it. That's all I have to say. I'm happy to answer questions as best I can. If I stop the screen share, I'll reappear. Yep, here I am. Beautiful Royal Observatory, Edinburgh.
Right. Thank you, John, very much. Thank you. I'll do the clapping on behalf of everyone. I just want to comment that the next call is in February 2021 instead of 2022, as your slide said.
Oh, yeah, sorry.
Yeah, well, I get the same feeling. It feels like the previous year didn't happen at all. Are there any questions to John related to this? I don't see any. Well, everything is clear. Excellent. So I hope everyone will now apply for OPTICON and ORP time. Very good. Okay, let's move on. Thank you, John. Let's move on to the radio part. And we have Haro Verkoter telling us about the radio perspective of the new proposal. Haro, are you there?
Yes, I am. I'm ready to share my screen.
Please.
Can you see my first slide?
Yes, we do.
Okay, great. Okay, so there's quite a lot of words there on the screen, but it's also actually what astronomers might want to do. So that's one box already ticked off. And to me, it sounds that this might be a possible easy workflow describing this whole process. Now, if you fill in a bit more detail, the multi-facility is obviously envisaged here, which sort of ticks off another box. Now, suppose that one of these facilities would be the European VLBI network, which is a centimeter wavelength, very long baseline interferometric array, using quite a loose definition of Europe because it includes sites in South Africa, China, and Korea. So adding such an array would actually tick off another box for free, leaving only the time domain. Now, let's for the moment assume that repeated observations, in our case, can count as time domain. And frankly, we're a good way on the way here. So let me now introduce JIVE. It is the Joint Institute for VLBI, European Research Infrastructure Consortium. And what it does, it provides support for different groups accessing, using, running the network, and doing science with the EVN. And it also has an active R&D department. So my name is Haro Verkoter, and I actually happen to work at JIVE. And we are a partner in the OPTICON RadioNet pilot project, which is starting next March. And our goal is indeed to add the EVN as a facility in this diagram. But actually what that means is that within ORP pilot, we will have to address these two topics as well for the EVN. And as mentioned before, the facilities seem to have their own North Star instance, and proposing to more than one facility is therefore not quite feasible. And again, as John also mentioned, and Jerry, it's using very old technology, and it's very, very hard to maintain. So the new tool will be developed, which allows users to propose for all the facilities in a single call. And Jive will be handling the European VLBI network side of those things. I have seen that for scheduling, some people can actually use the target and observation management manager. Now, in the EVN, we use something completely different, because instead you have to muck about with text file that drives a very old Fortran program. In the in the Jumping Jive project, Python wrapper was written for the SCED program. And the nice thing of that is that it allows you to replace bits of the code without rewriting the whole program in one go. But it is specifically this feature that we might actually allow to integrate this tool with the Tom toolkit. And that is what Jive will work on, hopefully providing an EVN Tom plugin. But there's always these that you have to consider. For one, we need to think about this. As a youngster, you know, I had a telescope like this, an optical 10 centimeter Newton reflector. Now, if you compare that to a professional radio telescope, the resolving power of that small thing is about 400 times larger than the 100-meter radio dish. Ouch. And there's another thing, because this thing is not the best camera around, as it were, if you put it like that. So one thing to beat both the resolution and the single pixel problem is to use a network of radio telescopes, which uses very long baselines and Earth rotation for up to 12 hours to synthesize a fraction of an aperture of a telescope of thousands of kilometers of diameter to be able to image usefully. Then there's another thing to concern, the actual size of the structures involved. These are massive chunks of metal. I mean, having to comply with local health and safety regulations means that chances of remote control are basically zero. There will always be human operators on site driving the telescope for you. And what to think about changing a filter? You might be thinking of something like this, a filter wheel. But in radio, this is typically changing an observing band. And actually, it can involve changing a receiver, which is again a big metal structure. And at certain telescopes, people have to go up in daylight with a crane to change this at the primary focus of the telescope. Further on, it is quite important to realize that the EVN is not a full-time VLBI array. And frankly, changing to VLBI mode for such a site takes a fair amount of time. And it is likely that in the call for proposals, there will be preset times and observing frequencies within which multi-facility and multi-frequency observations can be scheduled for the radio telescopes. And then there's this thing, analysis, because CCD images seem to be ready-made available, and some of them are already reduced, scientifically pre-processed. But FieldBI is actually an interferometer. So what we measure is some tracks in the Fourier domain. And the corresponding point spread function that you get out of that is pretty ghastly. It looks somewhat like this. And it means that after measuring a 2D Fourier transform, like we do, you actually need an inversion procedure to come up with an actual image. However, before the inversion can be done, many calibrations have to be applied. And in fact, the inversion process itself is an iterative one where many parameters that are possible that actually influence how the output image comes to look like. Now, within another Horizon 2020 project, the ESCAPE project, we are working on a Jupyter Notebook environment for our standard data reduction pipelines. Now, and whilst this is an improvement, it will never result in the best science image, unfortunately, without proper processing by a knowledgeable FieldBI scientist. So, summarizing, within the ORP pilot, Jive will work together towards integrating the EVN with the OPTICON methods where possible, and will benefit from work done in other Horizon 2020 projects. And I think that is all I have to say at this point. Thank you for your attention.
Excellent. Thank you very much, Haro. Are there questions to Haro? Good. Everything was clear. Very good. This is, different. This is very enlightening for, at least for me, and for optical people like us. We think images, that's images, but then it's not so straightforward in your word.
Nope. We are, as I said, we're involved in processes or projects where we try to improve on this, but yeah, it's not straightforward.
Right. But is there any hope in kind of getting closer to any automatization of the processing? I mean, mostly shortening the time and requiring less involvement of people in the chain.
I haven't even touched on, for example, to measure the 2D Fourier transform, the data from the telescope have to be combined from the individual telescopes. Since about 2006, we have embarked onto a project since then and are offering real-time FieldBI observations. So that was already a big game changer there. And that means that data is streamed from the radio telescopes at multiple gigabits per second these days, and correlated in our facilities in Dwingelo, the Netherlands, in real time. But still the calibration, some of the calibrations, we have to wait for the individual telescopes to upload their calibration data. And then it needs to be looked at because there are still, the calibration is not automated. We cannot do flat fielding or something like that. As you can imagine, over the time span of several hours, the atmosphere above the radio telescope changes, and that has a direct effect on the phases that we measure on our signal. That's for one thing. And another really weird effect is that even though we synthesize an aperture, the elements that make up the aperture look through different parts of the atmosphere. So the calibration, if you have 2 points in the aperture, you would have to apply different atmospheric calibration. And both of them vary on a different time scale. So these are things that we're trying to automate by, and in the scheduling, I've glossed over that, but in principle, a big part of making a good VLBI observing schedule for a source is to have a proper calibration scheme implemented so that you change between target and calibration sources on a regular basis, or that you can find an appropriate calibrator close to the target source. And unfortunately, the surface density of good radio astronomical calibration sources is not very high. So you'll always, what we do, the people scheduling VLBI observations, they will actually look at the science, what is a PI trying to achieve with this proposal, and tries to adapt the calibration scheme towards that.
Okay, so it seems like a challenge we stepped into, but we still have 4 years to figure it out. At least I have to learn new things. Anyway,
being able to propose from one location and even come up with a prototype schedule would already be a big step up.
That's right. That's the plan. Okay, thank you, Haro.
I see a raised hand, and I saw 2 before, but.
Well, I was looking at the virtual hands, but now I see John raising his real hand. Please, John.
Since Haro opened the door to this, this is my first ever astronomical telescope.
Ooh.
I still have it after 50 years. No, 55.
Do you still use it, John?
No, not much.
Not much. Well, you could at least have seen the conjunction between Jupiter and Saturn.
I use something else for that. I use my 50 centimeter, 50
okay,
millimeter, 50 millimeters for that.
Fine. Okay, I don't see any more questions or comments here. So excellent, we are on time. So let's take a break now, and let's meet again at 5:15 here. I will keep the Zoom open. I will keep the YouTube going, because if I stop it, then everything breaks. But I will. You can now take a break. If you want, you can log out from Zoom, and then you can come back. The Zoom will be here. See you in 20 minutes. Thank you. Hello, everyone. Let's get back here. We're back to after the break to the more, let's say, technical session. I will allow myself to chair this, even though I'm also a speaker. I think that will be the most convenient solution. And I'm looking for the next speaker, which is Rachel Street from LCO, and I can't see her. Rachel, if you are here, give me a shout. Okay. Well, if Rachel joins us later, then maybe we can move her talk to the after all the talks of this afternoon or evening even. So I will actually start. Right. I will share my screen. Partially, some things I will cover. They are partially in what Rachel was supposed to say, but I hope she can join us later. Okay, so this part will be on this time domain central coordination system, which has this horrible name, but that's just an official name in the grant proposal of ORP or OPTICON, and we internally we call it black hole TOM, and this is related to the TOM. So a target and observation manager, something what was designed by the LCO, Las Cumbres Observatory people, something what the LCO has been developing over the last decade or so. They've been, I think, pioneers at least in the optical part of astronomy. So I will mention it a bit later. I was hoping for an introduction from Rachel, but it's fine. We can do it later. Sorry, actually I forgot my headphones. So if you were saying something, then I probably didn't hear you. Sorry. Okay, so this is work done here in Warsaw at the Warsaw University Astronomical Observatory, but this is done in collaboration with Cambridge, with the Vilnius University and some other partners from OPTICON as well. So in terms of time domain astronomy, my point here is that there is always a time domain astronomy interesting target visible on the sky. And here I show the map, which is available. This map can be taken from Gaia Science Alerts website, and it's updated daily. You see the map of alerts found by Gaia alert system alone from all over the sky. There are other surveys, of course. There is Assassin, there is ZTF. There is going to be LSST fairly soon, which will monitor the southern sky down to 25th magnitude. So that's going to be this regime of astronomy is actually developing. And here we are talking about things which are changing rapidly, changing in a scientifically interesting way. You can think of time domain even broader than transients. Time domain is also eclipsing binary stars, right? Something what I've been working on in my early days, actually. Or my master thesis was actually on Cepheids. This is also time domain. You need a long time series of observations, of photometric observations. You can think of time domain also not only about photometry, but also about spectroscopy, about astrometry, multiple wavelengths, gravitational waves are also time domain astronomy. This is in contrast to, let's say, static astronomy, where you have an image, a very exquisite image taken by, let's say, by the Hubble Space Telescope or some high-resolution imager of VLT. You can study the details of clouds, of galaxies, and so on, or quasars, or something like this. This is different here. This is the time domain. This is the varying sky, right? We're now in this era of time domain, of checking what's changing on the sky. But our particular bit, what we've been developing within OPTICON, is related mostly to photometric, and this is what I'm going to concentrate on now. This is the photometric time domain. And Gaia alerts were kind of the main source of the targets of scientific interest. Well, yes, this is an example of one of the alerts found by Gaia, and the red points here are the Gaia data points. And here was an alert. So Gaia alert triggered saying that this star, which has been not changing for the last couple of years, suddenly got brighter. That's why it's interesting. And then the follow-up started, and you see how exquisite and dense the follow-up observations were. These are different multiple filters plotted together here, from I band to B band. They're in different systems. They were calibrated so that they match more or less on the same plot. I have to emphasize that there is also other survey data, which is Assassin. Assassin has been observing the same area on the sky, so we can also combine archival data for particular objects. So we can have two sources of time domain data, which is the follow-up observations, which are kind of on demand on the spot on that given object, actually per object, and then we can have surveys which deliver data, time domain data on multiple objects at once, and then you can cherry pick the one you are interested in. You see a huge list of contributors to that light curve, and we were very proud that this was eventually published last year, and we managed to find an explanation for this complex light curve as a binary microlensing event, which is actually rotating while lensing, right? That was quite peculiar and spectacular data to deal with. So since 2013, as Jerry already mentioned, we've been coordinating and encouraging to collaborate with a network of small and mid-sized telescopes. We normally put this boundary at 2 meters, which is not always the case. We have some telescopes which are larger than this, but that's more or less the idea of small and mid-sized telescopes. Everything larger is more complex, and it requires a team of people to run. Smaller telescopes, they are typically run by universities or smaller institutes. Very often they are robotic, so robotizing smaller telescopes is much easier than the big ones, of course. But this border where the cut is moving upwards slowly. Moreover, there's been many telescopes, small-sized telescopes, not only run by amateur astronomers, which they can provide beautiful data these days, but there are also very old telescopes, some of them 100 years old or so, or even more, which are still operational, and they serve as beautiful platforms for collecting data. You see the map here. Most of the telescopes we collaborate with are located in Europe and around Europe. This is not the best place, if you think about it, for astronomy. That's why the Europeans, they moved to Chile and to other locations where they place the telescopes, or they collaborate with other countries to have access to the much better sky. However, if you think about it, if you have a network of telescopes, there is always a chance at one spot in Europe, somewhere there will be clear sky. So you might collect the data at a given location, at a given moment of time, whenever you need it. So that was our principle to where we started. And as part of the collaboration, we organized this series of workshops, and now we are in the 11th workshop. Here you see posters and locations of all the workshops we had in the past. And you can actually see the archive of all the slides and videos and recordings from previous workshops on this website provided here. It's actually quite interesting to see the evolution of technology, of people's interests. And we started in 2010. It was 3 years before Gaia was launched. And now we are in 2021 when Gaia is actually finished its nominal mission. So this is quite amazing that we've been going through all this period of time. Excuse me. Okay, so what we've developed over those years is something what we called calibration server. It has the CPCS name, standing for, excuse me, Cambridge photometric calibration server. It's been in operation since 2013. The idea here was that it was receiving data from a network of the telescopes. It was receiving photometry and astrometry, but the data was already flat fielded, debiased, darks removed, and the preliminary instrumental photometry was done by expert people. As you think about it, not every person, not every astronomer even is capable these days of doing the photometry, instrumental photometry. And there is many telescopes, and people sometimes struggle of receiving very well to extract the photometric measurements out of their data. So we've been helping with that and trying to develop this. But generally, the idea was that we've been receiving these instrumental observations, and then we were placing them on a common scale, homogeneous, quasi-homogeneous scale. We've been trying to calibrate them. Some people call it standardize these light curves, these measurements, using survey data, which was obtained using the survey data as standards, right? And that worked fairly well. We were able to extract the light curves, as you see an example here. The event I showed you, the Gaia 16 AYE, was also solidly calibrated with these means. So that worked fine, but that was not what actually I think community needed. What we realized is that the huge bottleneck is the processing of the imaging at the photometric level. So flat fielding, debiasing, it is fine, everyone can do it. But later on, in order to get optimal photometry out of the images, it's a problem on its own, and each telescope has different issues and different problems. So this is what we've been working on for the last couple of years. And the idea was that we will build this CPCS 2.0, which we have built, and it's been under development since 2016. And it was running in kind of beta version under tests. So this was based on a photometric software called CCD-FOT. You will hear more from Przemek about this, how it is designed and how it works. So instead of instrumental photometry, we've been receiving the FITS files, and they were processed by the CCD-FOT. So this is where we were, but we never kind of progressed further to open it to a broader community. And then we came, well, I actually came across the TOM, the Target and Observation Manager Toolkit, a software which was developed by Las Cumbres Observatory. And I was actually fortunate enough to spend 3 months in LCO last year, well, sorry, 2019, when all this was initiated and all this work was, the TOM people, they presented, there was a workshop, and I was able to learn about the TOM, how this is designed. So instead of our lousy infrastructure we had before, we decided to build our infrastructure, the new infrastructure, based on TOM. And I'm going to show you the idea here. So TOM is capable of coordinating the telescopes. This is that's what LCO has been actually best at, was to control their network of telescopes scattered all around the globe. So this was built into TOM. So for us, it was essentially just take it readily. It was just ready made for us. So we definitely wanted to implement this. So TOM is capable of controlling multi-telescope observing requests. And then TOM is also capable of in ingesting data, FITS images from those telescopes. So this is exactly what we needed. And then we were able to build in our previous infrastructure of CPCS 2.0 into the TOM. And then TOM also acted as the data storage and access of the processed images. So these light curves, previously available through CPCS 1.0, now are all available through our TOM. So this is what we've been working on last year extensively. And this is the virtual access model we propose for the ORP, the new grant, and this is what we will be working on in next 4 years at least. So the flow is more or less the following. So you have surveys of different sorts. You have ground-based telescopes, you have radio surveys, you have satellite surveys, and they provide alerts typically via brokers. Brokers are the places where you can actually get the alerts from, not directly from surveys, but you can create your own filters, and then you can filter things out what you're interested in. And through these brokers, users get their targets of interest, and then they can provide observing requests. They can send it to our TOM, here officially called TDA-CCS, and then the TOM can coordinate, and this is the loop I showed you before, where there is network of telescopes. There are also telescopes which are available via transnational access, something that John has shown, and there is data flowing for all these telescopes back into the coordinate, the TOM, the black hole TOM, how we call it. And TOM processes all this data and then generates, and what's available for users actually is just this data, science-ready data products. So from the user point of view, they have the target of interest, they send the observing request, and more or less this bit is happening under the hood, and what they get in return is the science-ready data product. This is the dream plan we are working on now, but the first glimpses of this are already working, and you can actually see it. And the following talks after mine, they will show you more details of what we've came up with. So this is something what we call black hole TOM. The name for black hole TOM is, of course, because our group main scientific interests are microlensing black holes. That's where we started it, and I thought this is quite an exciting name, and it draws attention, and people will survive with this name being used. So this is just a glimpse of some screenshots of the black hole TOM and how it works. So it has the targets. This is a map of targets smiling at you here, and this is the sun here, the moon. So you can list the targets which are now they're listed there, and you can sort them by the observing priority. So depending of how urgent given target is, and combining it with the information how recently this target was observed. So it kind of tells you this particular target requires observations now, and this is the default ordering of the targets. When you click on a target, you can see more details, you can see all the information, you can see all the cross matches with ZTF, with Assassin, with AFSO, with other surveys as well, and then you can see the light curve. This is the Gaia data overlaid with ZTF data overlaid with follow-up data. So you have all the time domain information which are there in the world, which are publicly available. You have them displayed in one place, and this is your data which you can now start doing your science from. And as I said, you can upload a data product. You can upload your light curve if you have one. You can upload your individual image if you've just taken one. And of course, you can submit an observation request. You can submit it and then get the data back. The data gets processed, and then a data point will appear with your name on it. So the data points are tracked, who has observed them and who has produced them. So this is just a brief introduction to the black hole TOM. I'll stop here. I'll take questions if you have any at this point. And after my talk, we'll talk more about details, what can be done and how it works. So thank you. Are there any questions to me? Now it's me, chairperson, speaking. No questions. If there are no questions, there is a question from Nikos, please.
Hello, thank you for this nice presentation. So I would like a small comment, if you could, on the how do you define urgency of a target, priority?
Yes.
Thank you.
Well, there is. I didn't want to go into very details, so everything will be described in the manual as well. However, the target is urgent when the last observation was taken a long time ago, and there is a simple equation how urgent the target is. So you multiply it by priority. It's very subjective. So this, for some people, it can be seconds. It's needed within seconds. For some people, you just need to have it observed every other day or so, and that's the definition for them. So it depends. It's very target dependent, and we can. It's built into the TOM. We can work with any prioritization. Okay, Siegfried?
Thank you.
We can hear you. Unmute yourself.
My main question is if the facility to process fixed images is now fully finished, actually.
It is. It is. You're going to see it, and there's going to be a hands-on session led by Paweł Zieliński. There's going to be 2 hands-on sessions, actually. They will both be identical so that more people can attend them at different times, actually. So tomorrow and on Wednesday to see how it works in practice. But there will be more talks today explaining how it works. Yes.
I see that the manual has been updated too.
Sorry?
I see that the manual has been updated too.
Yes.
There's a new PDF.
Yes, there is a new manual.
Okay. I'm going to look at this.
Okay, great. Any more questions? To me? No. If not, then let's move on. The next talk will be given by Maja Jabłońska, who's a student here at the Astronomical Observatory in Warsaw, and she's been heavily involved in the development of the code and the black hole TOM as it looks, and she's going to show you some of the nice features of the code. Maja, are you with us?
Yes. Hello.
Hi. Please share your screen.
Of course. All right. Can you see my screen?
Yes, we do.
Great. So hello. I am an astronomy master's student at University of Warsaw, and as I have some experience with Python programming, because actually I have studied computer science before, I have been helping with Black Hole TOM, and I have to admit this has been the coolest project I have been doing because of its purpose. And I just want to give you a quick presentation and overview of some features I think are the most useful. And the first one is catalog names fetch, because as you may have experienced, the names for targets differ across catalogs. And because we aim to fetch data from many sources, it would be really useful to fetch these names as well. And in order to avoid the necessity to fill out the names manually, I have implemented an automatic query that queries, for now it's just 2 sources, but this can be, of course, and will be extended. And for now, it's transient name server, where it fetches TNS ID and Gaia alerts name, and if present, ZTF alerts name. And also Simbad, and where it checks for AAVSO name and Gaia DR2 ID. And just to show you that this feature indeed works, sorry, I clicked the... Okay, so I have created here new targets without any names associated with that. And you can see here that Gaia alerts name, ZTF, and TNS have been filled out automatically. Usually, Gaia targets don't have the ZTF alerts name, but this is due to the fact that they aren't the ZTF names sometimes aren't present on the TNS server. So there are going to be more sources, and even if for some reason the name isn't fetched, you can always update it manually, as it has been until this feature has been implemented. For example, usually in AAVSO you can also search by Gaia name, and it's also recognized. So here, after manual filling, you can immediately checking for new data, and it's all being processed automatically from this point on. I think this is the most useful one, but the other one, this is mainly due to the performance reasons, because sometimes there is a lot of data points, and as you can see, the interactive plot, where you can zoom to the data, you can see the hover, extra information. You can also filter out by the sources, because here, this example is not the one with a lot of data points, but sometimes there are really a lot of them. And the interactive photometry plot takes really a long time to load. And we have decided that on the main page, you just see the overview on the static plot, and then you can see the interactive one where you can do some more stuff. And also we wanted to make all this data available for download. And as you can see, maybe I will press pause because the thing is that when you work with many data sources, you might also want to have the information about the facility and the owner. And this is what I have also implemented, so that here this is data from AAVSO, so that you have all the information and of course all the photometric data points along with it in one place. This is done with Postgres views, so that it's fairly optimized and takes a reasonable amount of time to load. And yes, of course, all the data you upload yourself is also there in the data file you want to download. If you see the photometric file sample, I hope so, try the VHTOM out, you can see that in the comments you might also provide your own facility and your name, and this of course will be included as well. So this is meant to be compatible with all the sources you might need, and you want to I'm sorry for stuttering for a while. You want to use, and if you do have any questions, please don't hesitate to ask me any of them, whether by mail or on WonderMe or by Slack. And I'm really happy to hear any suggestions you might have, or any questions, or even features you would like to see, because as a former computer scientist, as a former developer, I should say, getting to know the astronomical world, I am really happy to use programming to contribute to the research. So we aim for VHTOM to be compatible with many sources to gather everything in one place. So I have been focusing on the features helping to do that for now. And I hope they will prove to be really useful. And thank you very much for your attention.
Okay, thank you, Maya, very much. Are there any questions now to Maya regarding the black hole Tom. Haro, and then Przemek.
Yeah, I was wondering, I see your interactive plots, etc. That is reminiscent of the virtual observatory toolkit. Is within the, and I was wondering if there's any reason why not to use those tools or protocols.
Do you mean the fact that the interactive plots are defaultly on the main site in the Tom toolkit?
For example, yeah, I think the virtual observatory is is an alliance. The International Virtual Observatory Alliance has been working for the last 20 years on interoperable data products and tools that actually allow you to query data from a multitude of data sources and overlay them. And so you can have, there's a table tool where you can view tabular data, and there's another plotting tool that, and they can interoperate. So if you select data in the table, then you get immediately them highlighted in the other tool.
I can answer. I can comment on this, Haro.
Okay.
I think I heard about virtual observatory a long time ago, but then, to be honest, I never looked into this in last 10 years or so, and I found generally it was kind of easier to look into the APIs of each individual survey, like ZTF and so on. But we will definitely have a look at this. Maybe there are still some things which we will benefit from. I'm pretty sure we will. So thanks for mentioning this.
Yeah, and just to add to that, if I may, in the ESCAPE project that I mentioned in my presentation, the European VLBI network archive is being opened up to the virtual observatory as well, so that you can actually find VLBI data and download data using VO protocols.
Right, right. This is very interesting. I'm not sure how flexible is that for time domain data. That has always been an issue, but we'll definitely have a look. So thanks for mentioning this. Przemek, you were next.
Oh yeah, thanks, Łukasz. Maya, I have a similar question regarding the plots. If you could go back to the place that you told us that you have to now click to open an interactive plot, because I would like to know what is the Python package, or what's the Python software that's responsible for creating these plots, for plotting them out on screen.
Well, this is kind of question, Przemek, sorry, but you can ask this on WonderMe. But I let Maya answer it very quickly.
Sure, all right. So for the interactive one, it's Plotly. And for the static one, quite classically Matplotlib. So I think Plotly Express is my favorite one. It's also used defaultly in the Tom toolkit, but actually I have made some changes and moved it to its separate window so that the page doesn't freeze up, because for a lot of data points it was really drastically slow.
Yeah, that's why I'm asking this question, because on the Gaia alert service, when you go into, let's say, Gaia 16 AYE, then the entire browser will freeze up because of the amount of data that have to be loaded up. So in the case of this interactive plot, did you try how many points can there be for the service to work optimally?
Well, I haven't, to be honest, I haven't really done any stress tests to figure out the number, but for example, for this target I have on this presentation, it would be reasonable, but for some targets that had 10 times the number of these data points, that would really take up a minute or something, so that it really throws up the whole page. So yes, this is why I have moved that to its separate window. And the interactive plots do take some time. And even though I have used a database view, so that's it should be faster, taken all from the one table. Also, I have used some small optimization with OpenGL that was suggested in Plotly, but that wasn't enough. So.
Guys, I have to interrupt you, and you can move this conversation to Wonder Me, because we have Pavel. You have half a minute to ask a question, and then Rachel as well.
Okay, actually, I have a question to you, Łukasz.
Okay.
Have you presented the website address to official Black Hole Tom?
No, deliberately.
Okay.
We will do it at some point today.
Yeah. Just yes. To keep this in mind to share the website link.
I'm surprised no one asked for this anymore yet. So yes, there's gonna be a new address, but the old address will work in a way that it will redirect you to the new portal. Rachel, please.
Hello. I just wanted to pick up on one of the previous comments about the IVOA interfaces for the underlying TOM toolkit. And I wanted to say how valuable the work of the IVOA is, and it is appreciated. At the moment, it's something that is on the to-do list for the TOM toolkit team, is to increase the IVOA interfaces that we have. So that is something that is on the development path for the next year or so. Thank you.
Great. So that will save us a lot of work. If TOM people do it, then we will just use it. That's a perfect world we live in, people, that, we just have ideas, and then TOM people, Rachel leading this, they just do it for us. So that's great. Okay. Can we now move to Pavel's presentation on more details about Black Hole Tom, and then yes, Pavel, please.
Yes, sure. Give me a moment to share the screen. Okay, I hope you can see my slides.
Yes, that's fine.
Okay, thanks. So I'm Paweł Zieliński, and I'm postdoc. Oh, sorry. And I'm postdoc at Astronomical Observatory in Warsaw, and I'm going to show you what's wrong with this. And I'm going to show you. Sorry, I have some problems with this presentation. Now should be better, I hope. No.
Don't do the slideshow, just the full screen.
Yeah.
It's a PDF.
Yeah.
Just full screen and then switch slides.
Yeah.
Yeah.
That was a reason. Okay, so I will show you how to upload the data on the Black Hole Tom. And please treat this presentation as a glimpse of this topic. More will be presented on 2 hands-on sessions tomorrow and on Wednesday. So I will show you how to upload the data in more detailed manner later. But now I would like to show you what can be done in this matter. So in addition to photometric viewing of the data and downloading this data, you can also upload your own data for specific target. To do that, you must go and click on the individual target And you see this screen with some photometric light curve. And to upload the data, you must use this white button. And everything should be quite easy, and there are some information which should help in uploading the data. You can add 3 different kinds of data. ASCII files, I mean text files, simple text file with your data, FITS images you have been taken by your telescope and instrument you use, or the table with photometric data in CSV format. But at first you must remember and pay attention on the one thing, namely the Calip server name must be provided. So the name which is the name with your individual target given in a calibration server database. Why? Because Black Hole Tom is connected with already existing calibration server. So don't be worried that some of your data will be lost. Everything on calibration server is there, and you can use it. But we encourage you to use Black Hole Tom, which is linked directly to calibration server, and all the data are also there. So they are sent there. So let's start with the ASCII files. To upload the ASCII file, you must choose this button and the first type of data product, instrumental photometry file. This is the example of such instrumental photometry file. So it is a file taken from Sextractor. So the format is the same as in Sextractor files with results of Sextractor processing. So at least 4 columns must be provided. The coordinates in degrees, alpha and delta, and the magnitude and error of magnitude, instrumental magnitudes. The rest of columns are not necessary, but you can add it as well. So all of you who are familiar with Sextractor, you just can send your results as a simple text file and upload it on Black Hole Tom. Of course, then you must complete the details of observations, namely the epoch of your observations, exposure time. You must select the matching radius to match the coordinates of your target with the coordinates taken from the catalog. Because to calibrate the data properly, we are using different various catalogs, and we must match the data which are uploaded together with the catalog data. There is also dry run option. When you switch on this option, the data will be won't be stored in the database. So the processing will be done until the end, but no data will be presented on the light curve as a point. Then you must select the observatory and select the filter to calibrate the data with the catalog. This is the filter from the catalog. So if you observe in visual filter, probably you want to use some V filters in APAS or USNO if available. The next option is to upload a FITS file. Black Hole Tom is dedicated for calibrated images. So when you do the observations and you have your raw data as a FITS file, just after the pre-reduction, dark bias subtraction and flat fielding normalization, you can upload this data to calibrate, to do the photometry and astrometry in automatic manner and to calibrate your instrumental magnitudes to the standard absolute magnitudes. So the second option must be chosen to do the automatic FITS file processing, and also we need to complete the details of observations, less details than in the case of ASCII files, because many of the data are already in the FITS headers, so they are read. They can be found in the FITS headers and read directly from them. But also we have a matching radius to be selected, filter. We want to match the data with the catalog. There is also dry run option, sorry, and we must also select the observatory where the data were taken. Where to check the results? There is another tab on the same place named data, and this tab is just to see the uploaded data, and all of the data uploaded on the calibration server can be viewed by everyone who is registered in Black Hole Tom, who has an account. But the checking the details and removing the data is possible only for your files. So for the registered users of Black Hole Tom, and you can remove only your data, and you can check the details of the FITS file or ASCII file processing on your files. So this is quite simple to find this, and this is the resulting page, resulting website with the photometric calibration. We have some informations which are the same as it was on the calibration server. So everyone who is familiar with the calibration server and who has sent the data there will know what is the meaning of this for sure. There is the final standardized magnitude of our target. The original FITS file is provided. The results of our photometric calibration in an ASCII file. So these two can be downloaded and reprocessed if you are not happy of these results. And there are also diagrams taken from the calibration server, which shows the matching to the catalog data in selected filter. If the dry run option is switched on, there is some comment that no data will be stored in the database. Okay, there is also a third possibility to upload a data as a table in CSV format. So, for example, if you want to use some photometric data and you want to upload the whole light curve from another database, for example, AFSO, you can do this by choosing this four type of data products, photometric time series. And this is the example of the table. So there is a time in Julian dates, filters and magnitudes with errors provided. And this is enough to upload the photometric data from another database, just to have everything in one place, for example, on one light curve. And you can also upload a spectra. It is very easy because to do this, you must have your spectra in an ASCII file. This is the example of such file with, so the wavelengths and fluxes must be provided. And by choosing the third option, spectrum as ASCII, this spectrum can be uploaded. And under the tab, which is called spectroscopy, you can see your spectrum, and you can also download the spectrum as a text file. So that's all. More will be presented on hands-on sessions on Tuesday, 6 p.m. Central European Time, and on Wednesday, 3 p.m. Central European Time. I hope you will be able to join us on WonderMe platform. And if you have any questions, do not hesitate to ask. Thank you very much.
Okay, thank you, Paweł. I hope people will skip the questions now, unless there's something urgent. Staszek wants to ask something very quickly.
Just a very short question. What's the list of keywords so BHTOM could recognize properly the parameters?
Which parameters do you mean?
Like time, filter.
Depending on the type of files you are providing.
Yeah, I mean FITS file.
FITS file. We just need to have the name of the observatory where the instrument, which corresponds to the observatory in this sense in our black hole TOM. And that's all, because before sending any FITS file, you must create an account, and then there will be a lot of questions, actually, what you want to do and which instrument you want to use, which data you want to upload. Based on this information, we are creating ops info file. You will see what is it in the next talk presented by Przemek Mikołajczyk, with the keywords, all keywords necessary to process the FITS files and to calibrate the data, to do the photometry, astrometry, and all what we need. So everything is actually in this ops info file. Przemek will say more about that.
Okay,
yes.
Thanks. So
Yes.
My question was too early.
Yes, let's continue. Thank you, Paweł, for your talk, and let's move on to Przemek now.
Okay, hi, everybody. I will share my screen with you. I hope you can see.
Yes.
Yes. Okay. So I think we are a little bit late, so I try to say everything as fast as possible. So I will tell you a little bit about the engine that's processing FITS images for BHTOM. The name of the software is CCDFOT, and it is a really easy to use pipeline dedicated for photometry. I say stellar, but you can easily do the photometry of galaxies. It may work in manual or automatic mode, so you can control the whole process, or you can try or you can trust the software and just count on it to do everything right. The idea was not to develop everything from scratch, but to use already tested software like SCAMP and Sextracton from Emmanuel Bertin and DAOFOT from Peter Stetson, as well as to use IRAF and PyRAF, which I'm sure that every astronomer used once, and then to implement Python scripts and so on. The pipeline was initially created as a reduction tool for the Białków CCD observations by Zbigniew Kołaczkowski, and later developed for sole purpose of running under BHTOM. The idea is to provide homogeneous method to reduce CCD observations, no matter from which telescope the data comes from. Okay, so the output of pipeline are 3 sets of photometric measurements. 2 are from DAOPHOT, which is aperture, group aperture photometry and profile photometry, and photometry from Sextractor as well, cron-like photometry. And very precise coordinate grid in FITS files is also provided. So it also works like astrometry.net, but using the most precise catalogs available, so Gaia. And if you would like to use the CD-Photon as standalone computer, you can also use many tools that are built into it. So like manipulating Fourier spectral light curves, creating CMDs, working with Gaia data. So you don't really have to use TopCat to download Gaia data, but instead of, you can use CD-Photon, which is equally good and even easier to use. Okay, so how does it work? So the only thing that you have to provide are your calibrated FITS images and the information about the telescope and instrument, and as well as the list of stars that you want to do the photometry on. This list of stars is also can also be downloaded automatically, and that also is being done by CCD4 for BHTOM. So calibrated FITS images supplied with the right keywords in FITS headers are then there is astrometry performed with the use of SCAMP and Sextractor, and then the astrometry is being validated to determine if we are really in the right field in the sky. And then 3 types of photometry are performed. So first Sextractor, then aperture photometry for DAOPHOT, and then profile photometry, which is the most tricky one, because you have to remember that there have to exist some set of stars, preferably bright ones, to determine the global PSF function for the entire image. But this is also done automatically by CCD-Photon. Then the Gaia astrometry with latest release is being performed, and the results can be sent automatically to BHTOM or any other service that you want to use. Here I present input data that has to be provided for the whole system to work. So there are actually two things that you have to remember about. First is your object name in your header. So let's say that we have IRS rock observations. So Gaia 16AYE is okay, but with the space in the beginning will give you an error. With some G16AYE also give you an error. So the object must be reservable by SIMBAT or Gaia Alerts database. Maybe in the future we can add some other databases if we have to. Now about what keywords have to be supplied in FITS headers. The whole dictionary that consists of all these keywords is probably already supplied on the BHTOM website, and you can download it and feed it in yourself. But the idea is really simple, that in the second column, there are keywords that are present in your FITS headers. If they are not, if some keywords is not present, you just leave it with dash, like organization in this example. Then you fill your values in the fifth column. And the thing to remember, the first position is to remember that longitude is positive when on the Western hemisphere. Then you have the second position regarding your keywords regarding time, start of exposure, and so on. Then in the third part is the most important part for you to fill in correctly. You should provide values for your gain, readout noise, saturation level, pixel scale, pixel reference coordinates, as well as the filter system and types of the way that we can recognize what type of image it actually is, because it may be not only like a scientific image, but also it can be a flat image that you also can process through CCD-Photon. But of course, you will not get any data points on the light curve. So if you have like some ambiguous keywords in your FITS headers, like 0, you can rewrite it to bias, filling the dictionary as presented here. The same with filters. If you don't have names of the filters but positions of the filters, you can rewrite it as well in this manner. Moreover, if you use 2 or more camera modes in your observatory, you can fill in every single mode that you want. I present here 2 modes with gain 9 and gain 6.7 electrons per ADUs, and as you can also differentiate between binning, read time from the CD array, and so on. And the last position is telescope limiting magnitude, if you would be so kind and provide as well approximate value for this. 4th, 5th, and 6th sections are much easier, because 6 is for the future for amateur astronomers which are not able to calibrate FITS image themselves, and they will be able to upload the entire night, and then the calibration will happen on our server, and that's basically it. I will help you via WonderMe, and maybe we can even organize some hands-on session for you to fill in your own dictionary. So the resulting files are FITS images with WCS coordinates supplied in headers, as well as standardized header values for all the fields that I presented in previous slides. One more good thing is that our pipeline already knows which of the measurements, is it profile, aperture photometry from DAOPHOT, or maybe sextractor photometry, is the best, and which one should be prepared to be uploaded to BHTOM, so it's CPCS 2.0 actually later. And the one processed single file processing looks like this in terminal. So it's really also easy to use for the standalone computer, so user can control every single aspect of the process. So here are the examples of already processed images with subtracted stars. You can see that there are some, that the software will do just fine with sparse fields, with dense fields, with the hydrogen cloud present as well. And if we display the image from Gaia in AYE, there are over 14,000 sources here in this image, and they were automatically subtracted without any interaction from my side whatsoever. So at the last slide, I will show you which of the observatories have been already implemented in BHTOM. So if your observatory is on this list, you can already start using BHTOM and upload FITS images. If not, this week should give you the opportunity to add your own observatory to BHTOM. If you have any questions, please ask them now or later. Thank you.
Okay, thank you, Przemek, very much. Are there questions? Yair, please.
Yeah, so you mentioned this is depends on IRAF, which is no longer supported. Is there any way to do this kind of stuff without IRAF at all?
Yes, yes. So in the beginning, the IRAF was the main software that we are using to do so many things with FITS files, like modifying FITS headers even. Now we have removed most of IRAF and PIRAF from the pipeline. Last routines will be removed this year for sure, because it's no longer developed. So yeah, the routines are pretty much written in Fortran for IRAF. So we plan to go totally IRAF-less in the next release. Yeah.
Great, thank you.
Welcome.
Siegfried. Siegfried, you're going to ask a question?
Yeah. This is a full Linux application, I believe.
It works for on Linux and Mac as well. This is the whole pipeline is written in Bash, but it's routines and other scripts are written in Fortran, Python, C, C++. So we try to move towards compiled languages for the most important routines, so the calculation time would go down.
There is no Windows version yet.
But we are working on a Python framework that could be run on Windows as well.
Okay.
Well, the main thing is that you don't even have to install CC-default. You can use CC-default, the version we have installed for you, you can access it via Black Hole Tom. That's the main message here.
And there's the underlying software actually, okay.
Yes, so you can do it from your browser.
You can do it from, you can upload any image you want, as long as your observatory is on the list, then it works just fine. It should work just fine. Of course, in the first weeks of the operations, we expect some problems, but over the last year, we really removed most of them.
Okay. Is there a separate download page too?
For now, no, because the installation of the software is quite complicated, but I will, of course, share the whole package with you and help you with the installation or give you some points to do it quickly.
Okay. Now let's move on to the next talk. Next talk about Mikołaj Kałuszyński, who will tell us more about the guts of the Black Hole Tom. Mikołaj.
Hello, everybody. Maybe I will start with some addition to what Przemek said before I find it. Actually, for those who are interested in the CC-default standalone, we will make probably the virtual machine available, and then all this struggling with installing the default and all these dependencies will be less important, and the system. Actually, it works like this in the Black Hole Tom facility. So we have the virtual machine, which is we can copy it and upgrade and freeze it. But okay, going back to my talk, I will talk about web services a bit in general, but then going to the application of web services to BH-Tom, and how you can use it also on the beginning to interface with BH-Tom. And this is last talk right now because there was a change, but I want to also to say thank you to the Account Lab team I'm a member of, and Artur Krawczyk and Tomek Maciejak, my colleagues, which worked together with me, as well as Łukasz, Paweł and Maja from Warsaw Observatory, Przemek from Wrocław University, my alma mater, and also people for having Tom, this beautiful software we are basing on. Okay, so web services. I will give you the definition, which is not the scientific, not the very pure definition, but the practical one. So the web service is a piece of software which functionality is exposed by HTTP protocol for other information systems. And usually when people are talking about web services, they are thinking about something like this. And just from this definition, the first thing is that it needs kind of web server to work, because it's exposed via HTTP protocol. And they're usually client agnostic. So there is a proper server, the service is proper server. So we are writing them in the way that anybody can write down their own client and follow your language and your definitions to connect to this server. And of course, in this communication between the web service and this HTTP communication, you need to have some common language to use. Usually, in the 99% of cases, this is either XML or JSON. And the word of XML web services, it's a huge subject with usually connected with Java, Java Beans, and things like this, and we'll skip it completely right now. And with cat chase to the Python web services. Because we are using Python in many scientific projects, this is like the best choice for the scientific applications. And even among the all the Python solutions, you have the very broad choice. And we can divide the platform, the frameworks for web services, the Python web services, for like two categories: the minimalistic, and they are very popular for making the small web services. Flask, Bottle, CherryPy, there are like examples of them, and you can write some web service, some function exposed by HTTP protocol in a couple lines of code. But then you need some user management, some database management, some protection, anything, and it's starting to be more and more complicated. And you can equally fast do such a web service using full-fledged framework like Parameter or Django. We are talking about here. We follow only the Django one. Which has the bootstrapping and builds the project for you with rich structure and many things. Like this is like the butter included approach. You have out of the box database support, user management, and many such things. And it's much closer to the application server architecture known from the XML and Java beans and things like this. It's much more extendable and so on. So going to the Django REST framework. This is the extension of Django, which is HTTP server itself. And it makes writing the web service is easy. Somebody, I think, makes some noise. I hope not. Okay, and as I said, it's the extension of the Django. So the web services can live along with the normal web pages, normal web application on the same server, for example. Another very interesting thing is the web browsable API. When you expose the web service, basically it's intended to be connected by other software. But during the development, it's if you have some such things like web browsable API, this is the web application which shows you the JSON API, and you can interact it via web browser, and it helps really a lot. And there are other properties of the Django REST framework. I will not elaborate more of them right now, because we do not have time. But believe me, the rapid development is really possible. I made for this workshop also the presentation of making web service ready and running from the scratch in 8 minutes. It's just the web service which serves the sky coordinates for the given objects and learns, it has a database of them, and learns for the new object asking the Sinbad database. You can see the video, there is a link over there. But right now there is just 1 minute from this video showing you this browsable API. When you see in here, you are navigating via the browser by the URLs used normally by the other software, and you see the JSON's answer, and you can interact and post some data. Right now, this is from this, and actually, you as well, it's the intended way you can interact via curl, for example. We are asking for some object, and it found the object, asking for another one which wasn't, which haven't been in the database, and we have the answer. And we can immediately check in the browsable API what is the list of objects in our database. Right here, we see that the object has been added. So it's the big advantage of Django REST framework for making web services available. Okay, and we are using web services a lot in BHTOM. Generally, here you can see the BHTOM can be accessed by the user using the HTTP GUI, so the normal web application, but also the observatory software can use it as a web service. This is this second arrow. And also BHTOM interface with CCDFOT, Przemek was talking about, via CCDFOT service, the web service we created for this, which lives in the same virtual machine when with the CCDFOT, another machine. And also the Cambridge Photometric Calibration server has the user interface, but also the normal ways is to access it as a web service, and BHTOM uses this method also. So this is about the CCDFOT, maybe a bit more, because this is the part I developed, but in here we can see like screenshot from the web page from of the API of CCDFOT, and we see some jobs which have been posted to CCDFOT. The job has some properties, status. There is a status. There are some files, and we can even observe like this, or using this interface, we can schedule the jobs for CCDFOT. And BHTOM also has the similar interface using also the REST framework. And in here you see the list of uploaded scientific products and with the same browsable API. And this is the method for automatization of uploads of feeds files, but also maybe photometry files and so on from your observatory. And actually, this is the next step for the observatory integration with BHTOM. There will be a test server which will be available for the developers of the observatory when they start, and on them this browsable API will be available, so they can play with this. Maybe there will be like demo BHTOM to make the development of the integrating easier. And in general, I see my time is over, so I will not go to the deeper details of the integration of BHTOM, which is probably the most interesting thing. But right now, I will not tell you much more about this. Just that it's going to be not that hard and probably easier than with CPCS itself. So thank you very much.
Thank you, Mikołaj. There was a question, a request actually from Yair to post the link to your video you mentioned. You can, if you could post it here in chat, but also on the Slack, where I encourage actually everyone to join the Slack channel, and we can use it for, you know, the chat here will get deleted while the Slack chat will remain available for a longer time. So thank you for this, Mikołaj.
Okay, thank you. Now I'm stop sharing and posting those links.
Are there questions? Are there more questions to Mikołaj? If not, then right, the link is here. Okay, thank you, Mikołaj. Now our last but not least talk will be of Rachel Street. Rachel, I hope you're with us this time. Yes, you are there.
Yep. And apologies that I did not make it earlier in the session.
Well, it is early for you anyway, so thanks for joining us.
Let me
Okay,
see if
here
I
to you.
can
Yeah.
share my screen. How's that?
That looks fine. Yep.
Great. Okay, let's go to full screen. Okay, so thank you for giving me a couple of minutes to give you a broader overview of the TOM toolkit, which the excellent Black Hole TOM has been developed from. This is a collaboration between the software team and the science team at LCO. So kudos to my many excellent collaborators there. Our goal was very generally that deriving science from survey streams is quite a challenge. A lot of them are now producing very large target lists very, very quickly. Many of the targets are not known in advance. They are genuinely true transients. And the ability to follow up those alerts very quickly as soon as they're announced is opening up new science areas. So the ability to connect these services is now a scientific priority. But the priority of the targets themselves may change very rapidly. And so there's a major follow-up chain which has to happen, which is demanding in and of itself, in addition to the survey itself. So you have a continuous stream of new targets with the real-time detection of new targets coming in all the time, existing targets constantly being re-evaluated, and you have many data coming in from many different sources, all of which has to be converged, collated, and analyzed. And you also have to arrange observations on a range of different timescales from the immediate to long-term monitoring. And those have to take place across a range of different facilities. And these days that could even involve multi-messengers as well as multi-wavelengths. So even the follow-up surveys are themselves terabytes of data and up to thousands of observations requested. And teams, as you've seen from the Black Hole TOM, the actual people behind each project can be distributed worldwide. And so when you're collating all of this data, you need a platform which is accessible to everybody as soon as the data is available. And so with all of these huge data streams flooding in, it's fairly clear that software is needed to help us manage all of these targets, observations, and data products, not just from the survey side, but from the point of view of the follow-up teams. And it was this that motivated the development of the TOM toolkit. And this was by no means the first project that developed a target and observation manager system. Many surveys, follow-up teams had done this before in many different areas of science, but looking at them, they were somewhat reinventing the wheel. They had a lot of common functionality, they weren't easily reusable, and it was easier to develop a core package which would support all of these use cases and be customizable, rather than having all astronomers reinvent the wheel when we are not software developers most of the time. And so that was the reason for building the TOM toolkit. It is open source. It's developed by our professional software team at LCO, but it's designed to be customizable. You should be able to deploy a TOM system that is quite fully functional right out of the box, but it also provides you with documentation and training. If you want to customize it for your own use, you can do that. But you can also get interfaces to commonly used services in astronomy without having to reinvent that wheel every time. And one thing that I particularly put emphasis on is the support community. There's lots of people now using TOMs, and we try and actively support the user community. So we have a public Slack channel by which you can go to that address at the bottom of the screen there to join. And our developers are on that Slack channel. We monitor it constantly and we answer user questions. And we'd be very happy to get your feedback. Thanks very much.
Okay, thank you very much, Rachel. That's great. Thing you're doing and you keep doing, and you're getting really better and better. I see there's so much development happening in TOM It's hard to catch up. Actually, we are still running some older version of Tom while there's been new developments, so we have to catch up. And I do recommend it. It can be applied to. You can build the Tom out of the box, as Rachel said. You can just run it. It's quite amazing, and we've used this for our thing as well. Thanks to you.
Thank you.
Right. So that would be it for today, and we actually made it on time. I'm really shocked and surprised, pleasantly surprised. So thank you all for all the speakers for keeping the time and making this first day of the workshop very interesting and inspiring. Thank you all of you for joining. We meet again tomorrow morning. It's a different time. Remember, every day it's a different time. We try to match different time zone. We start at 10 a.m. Polish time, so translate it to your tool, or you can use the workshop agenda. It does it for you. But there is this WonderMe platform which is open all the time, and I'm now posting on chat here the link to it, so that everyone who has access to it can. This is available only to registered people. So sorry for all the people on YouTube. Unfortunately, we cannot have every of you there. So please go there and discuss the talks and meet people, have an informal conversation, formal conversation, and so on. WonderMe is great. It will be useful, I hope. And I will stop here unless there is some urgent announcements from anyone else. I don't see any. Good. So I'll stop the recording, I stop the live stream, and I stop the Zoom, and I'll see you on Wonder, and I'll see you tomorrow. Thank you. Bye.
Thank you. Bye-bye.
Thank you, Lucas. Bye.
Thanks for the presentation.